The universe is expanding. Right now, while you're watching this video, galaxies are racing away from each other at hundreds of thousands of miles per hour. The space between them is stretching like fabric, being pulled in every direction. Every second, the universe grows larger. Every minute, distances increase. But here's the question that's haunted physicists for a century. If the universe is expanding, what is it expanding into? Is there something beyond, or is space infinite? Today, you'll get the answer. Complete, detailed, with explanations anyone can understand without a physics degree. By the end of this video, you'll know three things: why the question itself is built wrong, what will happen to galaxies in billions of years, and where the stars we see now will disappear to. Hit that like button right now, because the algorithm decides this video's fate in the first few minutes. And subscribe so you don't miss the next video about the cosmological horizon. Let's start with how we even discovered the universe was expanding, because just 100 years ago, scientists thought differently. Static universe, unchanging, eternal, stars and galaxies staying put for billions of years, nothing moving. That's what even the greatest minds believed. Even Einstein, the 1920s, California, Mount Wilson Observatory, Edwin Hubble, American astronomer. At his disposal, the most powerful telescope of the time, the Hooker telescope, mirror diameter 100 inches, a giant by 1920s standards. Hubble studied faint fuzzy patches in the sky. At first, nobody understood. Were these objects inside the Milky Way or something else? Hubble proved it. These were entire galaxies, billions of stars, beyond our galaxy. But the main discovery was ahead. Hubble measured light from these distant galaxies and noticed something strange. The light was shifted toward the red part of the spectrum. Redshift. What does this mean? When a light source moves away from you, light waves stretch, become longer, redder, just like the sound of a siren changes when an ambulance drives past. The Doppler effect. Only not with sound, but with light. Hubble looked at dozens of galaxies and saw the same thing. Redshift. All galaxies moving away from us. Moreover, the farther the galaxy, the faster it's receding. A pattern. Hubble's law. Distance directly proportional to recession velocity. Double the distance, double the speed. What does this mean? The universe is expanding. Galaxies flying apart from each other. And not because they're moving through space like cars on a highway, but because space itself is stretching. The fabric of the cosmos increasing in size, and galaxies rushing along with it. Imagine a balloon, dots drawn on its surface. Each dot is a galaxy. When you inflate the balloon, the surface stretches. Dots move away from each other, but they're not moving across the surface. The surface itself moves. That's exactly how universe expansion works. Space stretches. Galaxies move with it. Hubble's discovery turned cosmology upside down. The universe isn't static, it's dynamic, it changes. And if galaxies are flying apart now, they must have been closer in the past, even earlier, right next to each other. At the very beginning, everything was compressed into one point, hot, dense, incredibly small, and then an explosion, expansion, the Big Bang. The Big Bang theory was born from Hubble's observations. All right, the universe is expanding, fact established. But expanding into what? Here's where it gets really interesting. Because our everyday experience suggests if something's expanding, it must be expanding into something else. A balloon inflates into a room. The room exists in a house, the house on Earth, Earth in space. Everything expands into something bigger. But the universe, it contains everything, literally. All space, all time, all matter, all energy. If the universe is everything that exists, what can it expand into? Beyond it, there's nothing. Because beyond, there's no concept of beyond, no space, no time, nothing. Physicists say the question is built wrong. The universe doesn't expand into something. Space itself expands. Distances between objects increase. But beyond the universe, there's no external space it could expand into. Space is part of the universe. Time is part of the universe. Beyond it, these concepts simply don't exist. Hard to grasp? Let's try another way. Take the analogy of Earth's surface. Earth is finite. It has area, 197 million square miles. But Earth's surface has no edge. You can walk in any direction as long as you want, and you'll never reach an edge. You'll just return to the same spot. Earth's surface is closed on itself. The universe might work similarly, finite but without boundaries. Or another option, the universe is infinite, simply infinite, no edge, no end. Expansion of an infinite universe means distances between objects in this infinity increase. But infinity itself remains infinity. You can't make infinity bigger. It's already infinite. Objects inside it just move away from each other. Which option is correct? Finite universe without boundaries or infinite universe? Nobody knows for sure. Observations suggest the universe looks flat. Space geometry is almost perfectly flat. Parallel lines stay parallel. Triangle angles add up to 180 degrees. A flat universe could be infinite, but it could also be finite if it's closed in a special way we can't yet measure. While scientists debate the universe's shape, they agree on one thing: expansion is real, and it's accelerating. Yes, you heard right. The universe is expanding faster and faster. A discovery from the 1990s, 2011 Nobel Prize. Teams of astronomers studied distant supernovae, star explosions. These explosions are very bright, so bright they're visible billions of light years away, and they have predictable brightness, standard candles in space. Astronomers measured how far these supernovae were and how fast they're receding. Expected to see universe expansion slowing down. Gravity should break expansion. Galaxies attract each other. Should slow the spread. Logical? Logical. But results showed the opposite. Distant supernovae were dimmer than expected. This meant they were farther than they should be. Galaxies had receded to greater distances than theory predicted. Expansion isn't slowing, it's accelerating. Shock. Complete shock for the scientific community. What's making the universe expand faster? What force counteracts gravity? Scientists gave it a name. Dark energy, but the name doesn't explain anything. We don't know what it is. We only know it exists, and there's a lot of it. About 70% of all energy in the universe is dark energy. Dark energy acts like anti-gravity. It doesn't attract, it pushes apart. The more space, the stronger its effect. And here's the paradox. When the universe expands, more space is created. More space means more dark energy. More dark energy means even faster expansion. Positive feedback. Expansion reinforces itself. What happens next? In billions of years, expansion will become so fast that distant galaxies will start receding from us faster than light. Wait, can't nothing move faster than light? Right. Objects can't move through space faster than light. But space itself can expand at any speed. The speed of light limit doesn't apply to space expansion. When a galaxy recedes faster than light, its light can no longer reach us. Light will travel toward us, but space between us and the galaxy will expand faster than light can cross it. Like running on an escalator belt moving backward faster than you're running. You try, but you're riding backward. Such galaxies will disappear from our view forever. Their light will be stretched to infinity. Redshift will go beyond visibility. The galaxy becomes invisible, not because it's gone, but because information from it can no longer reach us. This is already happening. Right now, there are galaxies whose light will never reach Earth. They're too far. Space between us and them is expanding too fast. We don't see them, never will. They're beyond the observable universe. What's the observable universe? It's the part of the universe whose light has had time to reach us since the Big Bang. The universe is 13.8 billion years old, so we can see objects whose light traveled to us no more than 13.8 billion years. But space expansion complicates the calculation. The actual distance to the farthest objects we see now is about 46 billion light-years. Because while light traveled to us, space was expanding. The object moved even farther. The observable universe is a sphere with a 46 billion light-year radius centered on Earth. Beyond this sphere lies the rest of the universe, possibly infinite, but inaccessible to us. Light from there hasn't had time to arrive yet, or never will due to accelerating expansion. The cosmological horizon, the boundary of the observable universe. It's not a physical barrier, it's an information limit. Beyond it, there could be trillions of galaxies, countless stars, planets, maybe even life, but we'll never know, because information can't overcome expanding space. What's beyond the horizon? Maybe the same as here. Galaxies, stars, planets. The universe looks homogeneous on large scales. Cosmological principle. Anywhere in the universe on large scales, everything looks the same. No privileged center, no special places, everything roughly the same. If true, beyond the horizon is just continuation of what we see here. More galaxies, more structures, more of the same. But it could be different. Some theories suggest the universe is non-homogeneous on the largest scales. There could be regions with different matter density, different space properties, maybe even different physical laws. Multiverse, multiple universes, each with its own rules. Our universe is one bubble in an infinite foam of bubbles. Beyond the horizon might be other bubbles, unreachable, invisible, but existing. For now, it's speculation, beautiful speculation, but unprovable. We can't observe what's beyond the horizon, so we can't test it. Science requires observations. Without observations, only theory remains. Mathematics, philosophy, back to the observable universe, to what we can study. Expansion affects all cosmic structures, galaxies, galaxy clusters, voids, the cosmic web, giant network of galaxies connected by threads of dark matter and ordinary matter. Between threads are voids, huge empty regions. Universe expansion stretches the cosmic web. Voids grow larger. Threads stretch. Galaxies inside threads move apart. But within galaxy clusters, gravity wins. Clusters stay bound. Gravity is stronger than expansion on small scales. The Milky Way and Andromeda, two nearest large galaxies. Distance between them about 2.5 million light-years. They're not flying apart. On the contrary, they're approaching. Gravity pulls them together. In 4 billion years, they'll collide, merge into one giant elliptical galaxy. Universe expansion doesn't affect their approach, because gravitational binding between them is stronger than expansion's effect. Expansion is noticeable only at distances of hundreds of millions and billions of light years. Between galaxy clusters, where gravity is weaker, where space wins, where expansion rules, what happens to the universe in trillions of years? If dark energy continues acting as now, expansion will accelerate. Galaxies beyond our local cluster will disappear beyond the horizon, one by one. First the farthest, then closer ones. Eventually the sky will empty. In 100 billion years, observers on Earth, if any exist, will see in the sky only our local group of galaxies, Milky Way, Andromeda, a few dwarf galaxies. The rest of the sky will be black, empty, no distant galaxies. No cosmic microwave background. Information about universe expansion will be lost. Future scientists won't be able to discover the Big Bang because evidence will disappear beyond the horizon, even farther in the future. Trillions of years, stars will start dying, new stars will stop forming, gas will run out, galaxies will go dark, only cooling remnants will remain. White dwarfs, neutron stars, black holes, the universe will become dark, cold, empty. This is the heat death of the universe, state of maximum entropy, when all energy is evenly dispersed, no temperature differences, no energy flow, no processes, no changes, static dead universe. But that's after an unimaginably long time, after 10 to the power of 100 years, a number with 100 zeros. The universe's age now is only 10 to the power of 10 years. There's still unimaginably much time ahead, so much our minds can't grasp it. For now, the universe is alive, full of energy, full of structures. Galaxies shine, stars are born, planets rotate, life exists. We're here, observing, studying, trying to understand. And the main question remains, what is the universe expanding into? Answer, into nothing. Because the question is wrong. The universe is everything, all space, all time. Beyond it, there's no into what. There's only expansion of space itself, increasing distances between objects, stretching cosmic fabric. And what's beyond this fabric? Nothing. Because beyond doesn't exist. No outward direction, no external space, only internal, only universe, hard to accept, normal. Our brains evolved to understand objects our size, trees, rocks, animals, not infinities, not expanding spaces, not cosmological horizons. We're forced to use analogies, balloons, Earth surfaces, rubber bands. They help, but don't convey the full picture. Physics of universe expansion is built on Einstein's general theory of relativity. According to this theory, space and time aren't absolute entities. They're dynamic. They curve under mass and energy. Gravity is space-time curvature, and cosmological expansion is evolution of universe geometry over time. Stay with me, because we're not done yet. There's still an hour of material ahead, about space curvature, about universe shape, about distant galaxy fate, about changing physical constants, about quantum foam, about multiverse. This will be deep, this will be interesting. Stay with me. Part 2, Dark Energy and Supernovae, 12 on 22. Well, Einstein's equations predicted it, but nobody believed it, because accepting it meant accepting something impossible. Empty space has energy. Vacuum isn't empty. It pushes, it accelerates, it drives galaxies apart faster and faster. The late 1990s, two teams of astronomers, both hunting the same thing, proof that universe expansion was slowing down. The supernova cosmology project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory. The High Z supernova search team, led by Brian Schmidt and Adam Rees. Rivals, competitors, both convinced they'd measure deceleration. They studied type Ia supernovae. These are exploding white dwarf stars. When a white dwarf accumulates enough matter from a companion star, it reaches a critical mass, 1.4 solar masses, the Chandrasekhar limit. At that exact point, the star detonates. Every type Ia supernova releases almost identical energy. They shine with predictable brightness, standard candles scattered across billions of light years. Here's how it works. You observe a supernova. You measure its apparent brightness, how bright it looks from Earth. You compare that to its actual brightness, which you know because all type Ia supernovae are similar. The difference tells you distance. Dimmer means farther. Simple geometry. Then you measure redshift from the supernova's spectrum. Redshift tells you how fast the galaxy is receding. Distance plus recession speed equals expansion rate. Both teams expected the same result. Distant supernovae should be closer than their redshift suggests, because gravity should have slowed expansion. The universe should be decelerating. Galaxies should have traveled less distance than they would in a constantly expanding universe. The data came in. 1998. Confusion. The supernovae were dimmer than expected, much dimmer. They were farther away than they should be. The galaxies had traveled farther. Expansion hadn't slowed down. It had sped up. Both teams rechecked everything. Telescope calibrations, distance calculations, redshift measurements, statistical analysis. Every check confirmed the same result. The universe is accelerating, not slowing, accelerating. This made no sense. Gravity pulls. It slows things down. The Big Bang gave the universe initial expansion. Gravity should break it, gradually, over billions of years. Eventually, maybe the universe would stop expanding, maybe even collapse. The big crunch. That was the expectation. Instead, something pushes back, something stronger than gravity on cosmic scales, something invisible, undetectable, everywhere. They named it dark energy. The name explains nothing. It's a placeholder, a label for ignorance. We see the effect. We don't understand the cause. Dark energy makes up about 70% of the universe's total energy, not 7%, 70. The dominant component. Dark matter is about 25%. Ordinary matter, everything we can see, stars, planets, gas, dust, you, me, all of it combined, barely 5%. We live in a universe where 95% of the content is invisible and mysterious. The 2011 Nobel Prize in Physics went to Perlmutter, Schmidt, and Rees for discovering accelerating expansion. The Nobel Committee stated, for the discovery that the expansion of the universe is accelerating through observations of distant supernovae, the discovery that changed cosmology forever. What causes dark energy? Several theories compete. The most popular, dark energy, is the cosmological constant. Remember Einstein? In 1917, he modified his general relativity equations to keep the universe static. He added a term, the cosmological constant, represented by the Greek letter lambda. This constant counteracted gravity, preventing collapse. When Hubble discovered expansion in 1929, Einstein realized his mistake. A static universe was wrong. He abandoned the cosmological constant, reportedly calling it his biggest blunder. But the cosmological constant came back, because accelerating expansion needs explanation. If dark energy is the cosmological constant, it means empty space has intrinsic energy, vacuum energy, built into the fabric of space-time. As space expands, more vacuum appears. More vacuum means more energy. More energy means faster expansion, positive feedback, runaway acceleration. Quantum field theory predicts vacuum energy. Virtual particles constantly pop in and out of existence in empty space. These quantum fluctuations carry energy. When physicists calculate how much vacuum energy should exist, they get an absurd number, 10 to the power of 120 times larger than observed dark energy. The worst prediction in physics history. Either the calculation is wrong, or something cancels out most of the vacuum energy, leaving just enough to drive cosmic acceleration. Another theory, dark energy isn't constant. It changes over time. This hypothetical substance is called quintessence, named after the ancient Greek fifth element. Unlike the cosmological constant, quintessence varies in strength and density. Maybe dark energy was weaker in the early universe. Maybe it's getting stronger now. Maybe it will change again in the future. Quintessence opens wild possibilities. The universe's fate becomes unpredictable. A more exotic idea, phantom energy. This is dark energy that grows stronger as the universe expands. Not just constant energy per volume of space, but increasing energy density. Phantom energy leads to the Big Rip. Eventually, expansion becomes so violent that it tears apart galaxies, then solar systems, then planets, then molecules, then atoms, then atomic nuclei, everything ripped to shreds by space itself, stretching faster than any force can hold matter together. The Big Rip might happen in 20 billion years, or 50 billion, or never. We don't know. Some scientists question whether dark energy exists at all. Maybe general relativity breaks down on cosmic scales. Maybe gravity behaves differently across billions of light years than it does in the solar system. Modified gravity theories attempt to explain accelerating expansion without dark energy. These theories face challenges. They must match all observations: galaxy rotation, gravitational lensing, cosmic microwave background, supernova distances. Most modified gravity theories fail one or more tests. Dark energy remains the simplest explanation, Occam's razor, the hypothesis requiring fewest new assumptions. General relativity plus cosmological constant explains observations. We don't understand why the cosmological constant has its specific value, but it works mathematically. Understanding dark energy is cosmology's biggest challenge. It shapes the universe's future. If dark energy stays constant, expansion will continue accelerating forever. Galaxies will spread apart. Space between them will grow. Eventually, most galaxies will recede beyond the cosmological horizon, disappearing from view. The observable universe will shrink even as the actual universe expands. Distant light will be stretched into undetectable wavelengths. The sky will darken. Future civilizations will see fewer galaxies. In 100 billion years, observers might see only their local galaxy group. No evidence of the Big Bang. No cosmic microwave background. Cosmology would be impossible to discover. If dark energy strengthens over time, the Big Rip scenario unfolds. Space tears everything apart. First, galaxy clusters unbind, then galaxies, then star systems, then stars themselves, eventually even atoms. The universe ends in complete fragmentation, every particle isolated, no structures, no information exchange, Maximum entropy. If dark energy weakens or reverses, expansion might slow down again, perhaps even stop, then contraction. Gravity takes over. Galaxies fall back together. The universe shrinks. Temperature rises. Galaxies merge. Stars collide. Everything compresses back into a dense, hot state. The Big Crunch. The reverse of the Big Bang, maybe followed by another Big Bang, an oscillating universe, cycles of expansion and contraction stretching eternally. Current evidence favors constant dark energy, the simplest scenario. Expansion continues accelerating. The universe grows larger, colder, emptier, but measurements have uncertainties. Small changes in dark energy's strength over billions of years would be hard to detect. We need more data, more precise observations. The James Webb Space Telescope observes distant galaxies with unprecedented clarity. Future missions will measure expansion history across cosmic time. Maybe we'll discover dark energy evolves. Maybe we'll find a pattern, a clue to its nature. Dark energy connects to deep questions in physics. Why does vacuum have energy? Why is the cosmological constant so small compared to quantum predictions? Is there a connection between dark energy and the Higgs field? Does dark energy link to extra dimensions? String theory suggests hidden dimensions beyond the three spatial dimensions we experience. Could dark energy arise from physics in higher dimensions? The mystery deepens. Because dark energy isn't the only invisible component. Dark matter holds galaxies together. Dark energy pushes the universe apart. Both invisible, both mysterious. Together they dominate cosmic evolution. We measure their effects. We map their distribution. We calculate their influence. But we don't know what they are. Made of unknown particles, unknown fields, unknown physics? Imagine you're studying a machine. You see gears turning. You measure forces. You predict motion. But 95% of the machine is invisible. You only see 5%. That's modern cosmology. We see stars, gas, galaxies. We infer the rest from gravitational effects and expansion rates. It works. Predictions match observations. But the fundamental nature of the universe eludes us. Dark energy measurements come from multiple sources. Type Ia supernovae provide distance redshift relationships. Baryon acoustic oscillations in galaxy distributions reveal expansion history. Gravitational lensing shows how mass warps space-time. Cosmic microwave background patterns encode early universe conditions. All these independent methods agree. Dark energy exists. Expansion accelerates. The universe's fate tilts toward eternal expansion. Here's the beautiful part. Every measurement refines our understanding. Every observation constrains theories. Science advances through precision. Newton's gravity was close. Einstein's relativity was closer. Dark energy forces us closer still. Maybe the next breakthrough reveals deeper structure. Maybe space has layers. Maybe dimensions beyond four. Maybe quantum mechanics and gravity unify in ways we haven't imagined. But right now, we're stuck. Dark energy works in equations. It fits data. It predicts observations, yet its nature remains hidden. The cosmological constant explains measurements, but not physics. Why that specific value? Why not zero? Why not larger? These questions lack answers. Perhaps answering them requires understanding quantum gravity, merging general relativity and quantum mechanics, the holy grail of theoretical physics. Scientists try different approaches: string theory, loop quantum gravity, causal dynamical triangulations, emergent spacetime. Each framework offers potential explanations, none proven, none complete. The puzzle remains unsolved. Dark energy's true identity awaits discovery, maybe tomorrow, maybe in a decade, maybe longer. Meanwhile, the universe keeps expanding, faster each moment, driven by mysterious energy woven into spacetime itself. We ride this cosmic acceleration, temporary witnesses to a dynamic universe. And we ask questions, we build telescopes, we analyze data, we test theories, because understanding where we are, where we came from, and where we're going drives human curiosity deeper than any ocean, higher than any mountain, farther than any galaxy. Dark energy isn't just academic curiosity. It determines cosmic destiny. Will the universe expand forever? Will it collapse? Will it tear apart? The answer lies hidden in dark energy's properties. Properties we're still measuring, still debating, still discovering. Measuring the universe's expansion rate sounds straightforward. Measure distances to galaxies. Measure how fast they're receding. Calculate the ratio. Done. Except astronomers have been doing exactly that for decades, and they keep getting different answers. Too precise. Careful, independent methods give results that don't match. The discrepancy is small, about 9%. But in cosmology, 9% might mean we're missing something fundamental about how the universe works. The Hubble constant quantifies expansion. It tells us how fast space stretches. The units are kilometers per second per megaparsec. A megaparsec equals 3.26 million light-years. If a galaxy sits 1 megaparsec away, the Hubble constant tells you how many kilometers per second it's receding. If it's 2 megaparsecs away, double the recession propagation speed, 3 megaparsecs, triplet, linear relationship, simple math. Edwin Hubble first calculated this constant in 1929. His initial estimate was 500 kilometers per second per megaparsec, way too high. His distance measurements were wrong. Over decades, better telescopes and techniques refined the value. By the 1990s, estimates converged around 70 kilometers per second per megaparsec, close to the modern value. But getting that precision required extraordinary effort. Measuring cosmic distances is incredibly difficult. You can't stretch a ruler to distant galaxies. You need indirect methods, standard candles, objects with known intrinsic brightness. Compare actual brightness to apparent brightness. The difference reveals distance. Dimmer means farther. The challenge is finding reliable standard candles. Cepheid variable stars serve as excellent standard candles. These stars pulsate. They brighten and dim in regular cycles. The pulsation period directly relates to the star's intrinsic brightness. Longer period means brighter star. This relationship, discovered by Henrietta Leavitt in 1912, revolutionized distance measurements. Observe a Cepheid's pulsation period. Calculate its true brightness. Measure how bright it appears from Earth. Compute distance, geometry. Cepheids work well for nearby galaxies, within about 100 million light-years. Beyond that, they become too faint to observe clearly, even with powerful telescopes. For greater distances, astronomers use type Ia supernovae. These stellar explosions shine as brightly as entire galaxies for weeks, visible across billions of light-years. As discussed earlier, they have predictable peak brightness, making them ideal standard candles for measuring cosmic expansion. The Hubble Space Telescope revolutionized Cepheid observations. Its position above Earth's atmosphere provides crystal-clear images. Astronomers measured Cepheids in dozens of galaxies, some containing type Ia supernovae. This created a cosmic distance ladder. Nearby galaxies calibrated with Cepheids, distant galaxies measured with supernovae. The chain extends outward, linking local measurements to cosmic scales. Adam Rees and his team used this method. They measured Cepheids in nearby galaxies, calibrated type Ia supernovae, extended measurements to distant galaxies. Their result, 73 kilometers per second per megaparsec, precise within about 2%, published in 2019, later refined to 73.2 with even smaller uncertainty. This represents the local universe method. Direct measurements, climbing the distance ladder rung by rung. But there's another way to measure the Hubble constant, using the cosmic microwave background. The CMB is radiation left over from the Big Bang. When the universe was 380,000 years old, it cooled enough for atoms to form. Photons stopped scattering off free electrons. They traveled freely through space. Those photons reach us today as microwave radiation. The CMB fills the entire sky. Perfectly uniform temperature, about 2.7 Kelvin above absolute zero, except it's not perfectly uniform. Tiny temperature variations exist, about 1 part in 100,000. These fluctuations encode information about the early universe. Density variations, sound waves propagating through primordial plasma. The patterns reveal fundamental cosmological parameters, including the Hubble constant. The Planck satellite mapped the CMB with unprecedented precision from 2009 to 2013. It measured temperature fluctuations across the entire sky. Cosmologists analyzed these patterns using detailed models of cosmic evolution. The models include dark matter, dark energy, ordinary matter, radiation. They trace how structures formed, how the universe expanded from the Big Bang to today. The Planck team's result, 67.4 kilometers per second per megaparsec. Uncertain by less than 1%, extremely precise. Published in 2018. This represents the early universe method, indirect inference, model-dependent, based on physics 13.8 billion years ago, projected to the present. Two methods, both rigorous, both precise, both published in peer-reviewed journals. The values, 73.2 versus 67.4. The difference, about 9%, far larger than the measurement uncertainties, statistically significant at more than 5 sigma. In physics, 5 sigma means near certainty, less than 1 in 3.5 million chance of random fluctuation. This is the Hubble tension, cosmology's most pressing problem. Either one measurement is wrong, or our understanding of cosmic evolution is incomplete. The tension has persisted for years. New measurements from both methods keep confirming the discrepancy. Independent teams, different telescopes, improved techniques. The gap remains. What could explain this tension? Several possibilities exist. First, systematic errors in measurements. Maybe Cepheid distances have subtle biases. Perhaps we don't fully understand Cepheid physics. Different chemical compositions might affect pulsation periods. Dust between us and distant Cepheids could dim their light, making them appear farther than they are. Astronomers have checked these possibilities extensively. The measurements seem solid, but systematic errors are notoriously difficult to eliminate completely. Second, early universe physics might be different than models assume. The CMB method depends on theoretical models. These models make assumptions reactions, about dark matter properties, about early universe conditions, about how radiation and matter interacted. If any assumption is slightly wrong, the inferred Hubble constant changes. Maybe dark energy behaved differently in the early universe. Maybe dark matter has properties we don't understand. Maybe something unexpected happened between the CMB epoch and today. Third, new physics might exist. Unknown particles, unknown forces, unknown fields. The standard model of particle physics is incomplete. We know this. Dark matter and dark energy aren't explained. Maybe other components exist. Early dark energy is one proposal, a hypothetical energy field active in the early universe but not today. It would change expansion history, resolve the tension, but we have no direct evidence for early dark energy. Another idea involves changing constants. The fine structure constant governs electromagnetic interactions. If it varied slightly over cosmic time, atomic physics would change. Light from distant galaxies would behave differently. CMB patterns would shift. This could reconcile measurements. Some studies hint at possible variations, but the evidence remains controversial. Modifications to general relativity offer another avenue. Einstein's gravity works perfectly on solar system scales, on galactic scales with dark matter included, but maybe it breaks down on cosmological scales. Modified gravity theories attempt to explain cosmic acceleration without dark energy. Some of these theories also affect the Hubble constant. They're constrained by many observations. Most fail some tests, but the door remains open. The Hubble tension might reveal cracks in the standard cosmological model. Lambda CDM. Lambda represents dark energy, the cosmological constant. CDM stands for cold dark matter. This model fits almost all observations beautifully. Galaxy distributions, large-scale structure, CMB patterns, supernova distances, everything works, except the Hubble constant. That one parameter refuses to cooperate. Some scientists think the tension is real, new physics is required. Others remain cautious. Systematic errors might still lurk in measurements. The debate continues. More data will help. The James Webb Space Telescope observes Cepheids in unprecedented detail. Its infrared vision sees through dust. Its sensitivity reaches farther. New measurements from Webb might break the deadlock. Ground-based surveys contribute too. The Dark Energy Survey, the Sloan Digital Sky Survey, mapping millions of galaxies, measuring their distributions, constraining cosmological parameters independently. Gravitational wave observations provide another method. When neutron stars collide, they produce both gravitational waves and light. The gravitational waves reveal distance. The light reveals recession speed. Combine them to measure the Hubble constant. Early results show promise. More events will improve precision. The tension reminds us that science advances through contradictions. When observations don't match theory, something interesting is happening. Either we're measuring wrong, or we're learning something new. Both outcomes advance knowledge. Fixing measurement errors improves technique. Discovering new physics revolutionizes understanding. Imagine if the tension persists, if better measurements confirm the discrepancy. What then? Cosmologists must revise their models, add new components, modify assumptions, test predictions. This process drives science forward. Newton's gravity seemed perfect until Mercury's orbit didn't fit. Einstein's relativity solved it. Maybe today's tension points toward tomorrow's breakthrough. The Hubble constant seems simple, a single number, expansion rate, but it connects to everything. Dark energy strength, dark matter density, universe age, spatial curvature. Change the Hubble constant, and the entire cosmic picture shifts. That's why this tension matters so much. It's not just about one measurement. It questions our whole framework. Right now, cosmologists worldwide are working on this problem, analyzing data, testing theories, proposing solutions. Conferences debate the tension. Papers propose explanations. Observations accumulate. Slowly, the picture will clarify. Maybe measurements converge. Maybe new physics emerges. Either way, we're watching cosmology evolve in real time. The Hubble constant has been called cosmology's most important number. It sets the scale of everything. Distance estimates depend on it. Age calculations require it. Density measurements use it. Getting it right matters fundamentally. The 9% discrepancy might seem small, but it represents billions of years in age uncertainty, hundreds of millions of light years in distance error, significant differences in cosmic history. Understanding expansion rate means understanding fate. Faster expansion means younger universe. Slower expansion means older. The difference matters for structure formation, galaxy evolution, star formation history. Everything connects. That's why precision matters. Why astronomers obsess over decimal places. Every digit refines our cosmic story. The universe expands. Galaxies fly apart. Space stretches between them. Yet the Earth doesn't drift away from the Sun. The Moon stays in orbit. Your body doesn't inflate. Atoms hold together. Why does expansion affect some things but not others? The answer reveals a fundamental truth about cosmic scales. and the balance between competing forces. Expansion happens everywhere, every cubic meter of space, including the space between atoms in your body, between Earth and the Sun, between stars in galaxies. Space stretches uniformly. So why don't we notice it locally? Because gravity overwhelms expansion on small scales. The gravitational binding between massive objects is far stronger than the weak tug of expanding space. Consider Earth's orbit around the Sun. Gravitational force holds Earth in place, about 3.5 times 10 to the 22nd newtons. That's 35 followed by 21 zeros. Enormous force. Compare that to expansion's effect on the Earth-Sun system. The space between them expands by roughly 1/10 billionth of a meter per year. Utterly negligible. Gravity wins by a factor of trillions. Earth's orbit remains stable. The planets will continue their dance around the Sun for billions of years, completely unaffected by cosmic expansion. The same applies to atoms. Electromagnetic forces bind electrons to nuclei. These forces are incomparably stronger than cosmic expansion at atomic scales. Protons and neutrons stay locked in nuclei via the strong nuclear force, the most powerful force in nature. Expansion can't compete. Atoms remain intact. Molecules hold together. Chemistry works. Life exists because fundamental forces overpower expansion at small scales. When you breathe, when your heart beats, when neurons fire in your brain, expansion plays absolutely no role. The forces that govern biology operate on scales where expansion is completely irrelevant. Even stars resist expansion internally. Gravity crushes stellar material inward. Fusion pressure pushes outward. These forces balance perfectly. Expansion barely registers. A star like the Sun experiences essentially zero expansion effect. Its gravitational self-binding is immense. The Sun will die from running out of fuel in about 5 billion years, long before expansion affects its structure. When the Sun becomes a red giant and swallows the inner planets, that's gravity and thermodynamics at work. Expansion has nothing to do with it. Galaxies tell a similar story. The Milky Way contains hundreds of billions of stars. Dark matter provides most of the mass, creating a deep gravitational well. Stars orbit the galactic center in stable paths for billions of years. Expansion doesn't tear the galaxy apart, because gravitational binding energy far exceeds expansion energy. The galaxy behaves as a single bound system. Expansion slides past it, unable to grip anything gravitationally tied together. Our solar system orbits the galactic center at about 220 kilometers per second, completing one orbit every 225 million years. This motion has nothing to do with cosmic expansion. It's purely gravitational dynamics within a bound structure. Here's where things get interesting. The Milky Way and Andromeda galaxy sit about 2.5 million light-years apart. That's close by cosmic standards. They're gravitationally bound to each other. Mutual attraction pulls them together. They're actually approaching at about 110 kilometers per second. In roughly 4 billion years, they'll collide. When I say collide, I mean something very different from what you might imagine. Stars are so far apart that direct collisions between individual stars are extraordinarily rare. The average distance between stars is measured in light-years. Even during a galactic collision, stars mostly pass through the spaces between other stars like two clouds of gnats interpenetrating. But gravitational interactions will reshape both galaxies dramatically. They'll orbit each other multiple times over hundreds of millions of years. Tidal forces, the differential pull of gravity across extended objects, will stretch spiral arms. Gas clouds will compress from the gravitational disturbance. Compression triggers star formation. New stars will ignite by the billions. The night sky will blaze with stellar nurseries. Eventually, after multiple passes and perhaps a billion years of interaction, the galaxies will merge into a single massive elliptical galaxy. Astronomers have already named it Milkomeda, a combination of Milky Way and Andromeda. This collision happens despite cosmic expansion because gravity wins at this scale. The gravitational binding between Milky Way and Andromeda generates enough force to overcome local expansion. They inhabit the same gravitationally bound structure called the local group, a cluster of more than 50 galaxies. Most are small dwarfs, orbiting the two giants like moons around planets. The Large Magellanic Cloud, visible from the southern hemisphere as a fuzzy patch, is a satellite galaxy currently orbiting the Milky Way. The Small Magellanic Cloud is another. These dwarf galaxies are gravitationally captured, slowly spiraling inward, and will eventually be absorbed by the Milky Way. The entire local group spans about 10 million light-years. Everything within this region stays together. Expansion doesn't separate local group members because their mutual gravitational attraction is strong enough to resist. Think of it like a cluster of boats tied together with strong ropes. Even if the ocean current tries to pull them apart, the ropes keep them bound. Gravity is the rope. Expansion is the current. On this scale, the ropes hold. Galaxy clusters represent the largest bound structures in the universe. Some contain thousands of galaxies spanning tens of millions of light-years. The Virgo cluster contains over 1,000 galaxies about 55 million light-years away. The Coma cluster has thousands more at 320 million light-years distance. These structures stay coherent because their combined gravitational mass creates binding energy greater than expansion energy. Galaxies within clusters orbit around the cluster's center of mass. They collide and merge over billions of years. Hot gas between galaxies, heated to millions of degrees by gravitational compression, fills the space. This intracluster medium glows in X-rays, invisible to optical telescopes but bright to space-based X-ray observatories. The cluster evolves as a unit. Expansion affects the space between clusters but not within them. This is the critical scale transition. Within about 100 million light-years, if there's enough mass, gravity dominates. Beyond that, in the vast spaces between clusters, expansion takes over. Between galaxy clusters lies something remarkable. Voids, enormous empty regions. The largest voids span hundreds of millions of light-years. They contain very few galaxies, almost empty space. The Boötes void, discovered in 1981, spans 330 million light-years and contains only about 60 galaxies, where we'd expect thousands based on average density. These voids are where expansion dominates completely. No gravitational binding holds anything together. Space stretches freely. Voids grow larger over time. As the universe expands, voids expand faster than average because they lack mass to resist. The cosmic web structure becomes more pronounced. Filaments and clusters remain relatively compact. Voids balloon outward. This creates an interesting asymmetry. Dense regions stay dense. Empty regions become emptier. The universe develops more contrast. Galaxies cluster more tightly in filaments and nodes. Voids expand more rapidly. Over billions of years, the cosmic web becomes more dramatic. Long filaments of galaxies connecting dense clusters, separated by growing voids. The structure coarsens. Large-scale patterns become more prominent. Imagine a sponge being stretched. The solid parts stay solid. The holes get bigger. Now let's talk about scales. At what size does expansion overcome gravity? The boundary is fuzzy, but rough numbers help. Within a few million light-years, gravity usually wins if there's significant mass. Beyond 100 million light-years, expansion typically dominates. The transition zone depends on mass distribution. High-density regions stay bound at larger scales. Low-density regions expand more easily. Dark matter plays a crucial role in this balance. It provides most gravitational mass in galaxies and clusters. Without dark matter, galaxies wouldn't have enough mass to stay bound. Visible matter alone isn't sufficient. Stars and gas would fly apart. Galaxies would dissolve into scattered stars. Dark matter halos extend far beyond visible galaxies. These halos provide the gravitational glue holding everything together. They determine where gravity wins and expansion loses. Measurements from galaxy rotation curves, gravitational lensing, and velocity dispersions in clusters all confirm dark matter's presence and dominance. The future of this balance depends on dark energy's strength and behavior. If dark energy remains constant, like the cosmological constant, bound structures stay bound forever. Galaxies and clusters resist expansion indefinitely, but unbound regions, the voids and intergalactic space, continue expanding. Clusters drift farther apart. Eventually, each cluster becomes isolated. No more galaxy collisions between different clusters. The universe fragments into isolated islands. Each cluster becomes its own universe in a sense, completely cut off from all others. If dark energy strengthens over time, the situation becomes more dramatic. This is the Big Rip scenario. Phantom energy, increasing energy density as space expands. The equation of state parameter W drops below -1. Eventually, expansion becomes so violent that it overwhelms all forces. The timeline unfolds in stages. First, galaxy clusters unbind. Galaxies separate from each other. The gravitational bonds holding clusters together snap. Then individual galaxies break apart. Stars scatter into intergalactic space. The Milky Way would dissolve into billions of independent stars drifting through expanding void. Next, solar systems dissolve. Planets drift away from their stars. Earth would spiral away from the sun. The moon would escape Earth's orbit. All planetary systems throughout the universe would come undone. Then stars themselves explode, not from internal processes like supernovae, but from space expanding so rapidly within the star that it tears the stellar material apart. Stellar cores fragment. The Big Rip becomes catastrophic at this stage. Finally, even atoms rip apart. Electrons tear away from nuclei. Atomic bonds shatter. Molecules disintegrate. Then atomic nuclei themselves fragment. Protons and neutrons separate. Perhaps even quarks within protons tear apart. The universe ends in complete fragmentation. Every particle isolated. No structures of any kind. No information exchange. Maximum entropy achieved through total separation rather than thermal cosmological equilibrium. The Big Rip depends on the equation of state of dark energy. Current measurements suggest W equals approximately -1, consistent with the cosmological constant, but uncertainties exist. We can't completely rule out W slightly below -1. If W equals -1.1, the Big Rip might occur in about 20 billion years. If W equals -1.5, maybe 50 billion years. Precise measurements of dark energy's properties will determine whether this fate awaits us. Most scientists consider the Big Rip unlikely based on current evidence. The cosmological constant scenario seems more probable, but we must remain humble. Dark energy remains mysterious. Its properties could surprise us. Future observations might reveal evolution in dark energy's strength. The James Webb Space Telescope observes distant galaxies with unprecedented precision, measuring their distances and recession velocities more accurately than ever before. These measurements constrain dark energy's equation of state. Each new data point narrows the possibilities. For now, gravity holds local structures together. The solar system orbits serenely. The Milky Way spins majestically. Andromeda approaches inexorably. Galaxy clusters maintain their coherence. Life continues on Earth, untroubled by cosmic expansion. We exist in a cosmic sweet spot, large enough for interesting structures to form, small enough for gravity to bind matter together. If expansion were much faster initially, no galaxies would have formed. Matter would have dispersed too quickly. If it were much slower, the universe might have collapsed already, ending in a big crunch before stars and planets could form. We find ourselves in a universe where both gravity and expansion play significant roles. Gravity builds structure, collects matter into stars, planets, galaxies, creates the conditions for complexity and life. Expansion spreads it out, gives the universe room to evolve, prevents immediate recollapse. The tension between them creates the cosmos we observe, a universe old enough for stars to form and die multiple generations, young enough that stars still burn brightly, large enough for billions of galaxies, small enough that we can see them and study them, balanced between contraction and runaway expansion, poised in a state that allows observers to exist and ponder their existence. Understanding this balance explains why cosmology focuses on the largest scales. The physics that matters for cosmic evolution happens across billions of light years. Local physics operates in regimes where gravity dominates. But cosmology looks beyond into the realm where expansion matters, where dark energy shapes destiny, and where the ultimate fate of everything hangs in the balance. Look up at the night sky. Every photon hitting your eye carries information. Light from distant stars, galaxies billions of light years away, each one a messenger from the past. But there's a limit to how far we can see, a boundary beyond which no light can reach us, the cosmological horizon, the edge of the observable universe. And here's the strange part. This boundary exists not because space ends, but because time is finite and space expands. The universe is 13.8 billion years old. Light travels at 300,000 kilometers per second. Simple math suggests we can see objects whose light traveled for 13.8 billion years. So the observable universe should be 13.8 billion light years in radius, a sphere 27.6 billion light years across with Earth at the center. Logical, straightforward, completely wrong. The actual radius of the observable universe is about 46 billion light years, nearly 3 times farther than naive calculation predicts. How is this possible? The answer lies in expansion. While light traveled toward us, space itself stretched. The object that emitted the light moved farther away, not through space, but with space. By the time the light reaches us, the object sits much farther than when it emitted the photon. Imagine you're on a moving walkway at an airport. You walk toward the exit, but the walkway moves in the opposite direction. You're moving forward relative to the walkway, but the walkway carries you backward relative to the airport. Your net progress is less than your walking speed. Now reverse it. You walk forward. The walkway also moves forward. You reach the exit faster than walking alone would allow. That's photons traveling through expanding space. The photon moves at light speed. Space expands behind it. The starting point moves farther away. The distance light actually crossed is much greater than light speed times travel time. Here's the detailed calculation. A photon emitted 13.8 billion years ago, right after the Big Bang, traveled through expanding space. During its journey, space stretched continuously. The object that emitted it moved farther away due to expansion. Today, that object sits about 46 billion light-years away. The photon traveled for 13.8 billion years, but crossed a distance that grew to 46 billion light-years due to expansion occurring during the journey. This defines the observable universe's edge, the particle horizon, the cosmological horizon. Beyond this horizon lie regions whose light hasn't had time to reach us yet. Not because light travels slowly, light speed is absolute, but because the universe hasn't existed long enough for light from those regions to cross the expanding space between us. Every second that passes, light from slightly farther farther regions reaches us. The observable universe grows, but accelerating expansion complicates the picture dramatically. The cosmological horizon represents an information boundary. Everything within this boundary can potentially be observed. Everything beyond it cannot, at least not yet. But acceleration changes the rules. In a decelerating universe, the horizon would simply expand. More regions would become visible over time. But dark energy drives acceleration. This creates a second boundary, the event horizon. The event horizon marks regions that will never become observable, even given infinite time. Galaxies beyond the event horizon recede faster than light can travel through expanding space. Their light will never reach us, ever. The distance to the event horizon depends on dark energy's strength. If dark energy remains constant, the event horizon sits about 16 billion light-years away, closer than the particle horizon. This means galaxies currently visible will eventually disappear. Think about that. Galaxies we see today will vanish, not because they die, not because they move through space, but because space between us and them expands so rapidly that their light can no longer reach us. The light gets stretched to infinite wavelength, red-shifted beyond detection. The galaxy crosses the event horizon and disappears from view forever. This process happens gradually but inevitably. The farthest galaxies we see today have redshifts around z=11. That means the light we receive is stretched to 12 times its original wavelength. These galaxies existed when the universe was only 400 million years old. We're seeing them as they were 13.4 billion years ago. But due to expansion, they're now about 32 billion light-years away, and they're receding at enormous velocities. Eventually, perhaps in a few hundred million years, their light will become too faint and too red-shifted to detect. They'll slip beyond our ability to observe. Closer galaxies will follow. The Virgo cluster, currently 55 million light-years away, will remain visible for trillions of years. But galaxies billions of light-years distant will disappear much sooner. The observable universe appears to grow as light from farther regions reaches us. But simultaneously, the number of observable galaxies decreases as distant galaxies cross the event horizon. We're in a transitional era. The universe is old enough to see a vast cosmos, young enough that most galaxies remain visible. In 100 billion years, the situation changes dramatically. Most galaxies beyond the local group will have disappeared beyond the event horizon. Observers on Earth, if any exist, will see a much smaller universe. The Milky Way and Andromeda will have merged into Milkomeda. A few dwarf satellite galaxies will orbit nearby. But the rest of the sky will be black, empty, no distant galaxies, no quasars, no galaxy clusters, just darkness. Even more troubling, the cosmic microwave background will fade. The CMB, that faint radiation from the early universe, will be red-shifted beyond detectability. Future astronomers won't be able to observe it. They won't have evidence for the Big Bang. They won't be able to measure the universe's expansion history. They won't know dark energy exists. Their observable universe will consist of one large galaxy surrounded by emptiness. They'll develop different cosmological models based on limited evidence. They might conclude the universe is static, small, and eternal, just as we once believed. This raises a profound question. What are we missing right now? What evidence has already disappeared beyond our horizon? What conclusions might we draw incorrectly because crucial information is unavailable? The universe we observe represents a narrow window in cosmic history. Earlier, the universe was too young and too small for complex structures. Later, it will be too old and too expanded for comprehensive observations. We exist in a golden age of cosmology, a brief period when the universe is observable, complex, and not too spread out. The horizon also affects causality. Regions beyond the horizon cannot influence us. They're causally disconnected. Events there have no impact here. This seems strange. If the universe is connected, shouldn't everywhere affect everywhere else? But infinite light speed would be required for instantaneous causal connection. Light speed is finite, therefore causality is limited. The horizon marks that limit. This explains a puzzle about the cosmic microwave background. The CMB is incredibly uniform. Temperature varies by only 1 part in 100,000 across the entire sky. Different patches of sky have nearly identical temperatures, but some of these patches are so far apart that light hasn't had time to travel between them since the Big Bang. They've never been in causal contact. How can they have the same temperature? They couldn't have exchanged energy or information to equilibrate. Cosmic inflation solves this. In the first fraction of a second, the universe expanded exponentially. Regions that are now separated by billions of light-years were once in close contact. They equilibrated to the same temperature. Then inflation stretched them apart faster than light. They've been causally disconnected ever since, but they retain the same temperature from their pre-inflation contact. The CMB uniformity uniformity testifies to inflation's reality. The horizon also limits structure formation. Galaxies and clusters formed from density fluctuations in the early universe. These fluctuations had maximum sizes determined by the horizon at that time. Nothing larger than the horizon could exist as a coherent structure. This predicts a maximum size for cosmic structures. We observe galaxy clusters, superclusters, and the cosmic web. The largest structures span hundreds of millions of light-years. They match predictions based on horizon physics during the era when they formed. Understanding horizons clarifies misconceptions about expansion. People often ask if the observable universe is 46 billion light-years in radius, and objects at that distance are moving away faster than light. Doesn't that violate relativity? Special relativity says nothing can move through space faster than light. True, but special relativity applies to motion through space. Expansion is different. Space itself grows. Objects carried by expanding space aren't moving through space. They're stationary in their local reference frame. Space stretches between them. No relativity violation occurs. Another way to think about it, relativity limits relative velocity between objects that can send signals to each other, causally connected objects. But objects beyond the horizon aren't causally connected. They can't send signals. Relativity doesn't constrain their relative motion because they can't interact. The speed of light limit applies within causal contact. Beyond the horizon, it's irrelevant. The observable universe is not the universe. This bears repeating. The observable universe is the region from which light has reached us. The actual universe might be much larger, perhaps infinite. We don't know. We can't know. Direct observation is impossible, but we can infer. If the universe has curvature, we could calculate total size even without seeing all of it. Current measurements suggest the universe is very close to flat. Flat geometry can extend infinitely, so the universe might be infinite. We'll never prove it, but it's consistent with observations. Some speculate about what lies beyond the horizon. Three main possibilities exist. First, more of the same. The universe continues with similar properties. Same laws of physics, same types of galaxies. Homogeneity and isotropy extend indefinitely. This is the simplest assumption. The cosmological principle applied universally. Second, variations exist. Beyond the horizon, conditions might differ. Different matter densities, different dark energy strengths, different structure distributions. These regions would be invisible to us, but they might exist. Perhaps vast voids with almost no matter, or incredibly dense regions forming superclusters we can't observe. Variation seems plausible. Why should the universe be perfectly uniform everywhere? Third, fundamentally different physics. If the multiverse idea is correct, our observable universe might be one bubble in a vast ensemble. Other bubbles could have different physical constants, different particle masses, different force strengths, different numbers of dimensions. These alternate universes would be forever beyond observation, causally disconnected, eternally unknowable, fascinating to speculate about, impossible to verify. The horizon defines what science can study. Science requires observation, no science. Regions beyond the horizon lie outside scientific reach. Philosophy and speculation can ponder them, mathematics can model them, but empirical verification is impossible. This frustrates some scientists. They want to know everything. But the universe has other ideas. It imposes fundamental limits on knowledge, yet science continues advancing. Each new observation refines our understanding of the observable universe. Better telescopes reveal fainter, more distant objects. More sophisticated detectors measure subtler signals. Improved theories explain more phenomena. The horizon sets ultimate limits, but we haven't reached those limits yet. Much remains discoverable within the observable universe. Decades or centuries of research lie ahead before we exhaust accessible knowledge. The cosmological horizon reminds us of our place. We inhabit one small planet orbiting one ordinary star in one galaxy among hundreds of billions. Our observable universe contains perhaps 2 trillion galaxies. Each galaxy contains hundreds of billions of stars. Each star might have planets. The numbers are staggering. Yet this represents only what we can see. Beyond the horizon might lie infinitely more, or nothing. We can't tell. We're confined to our observable patch. Permanent cosmic islanders, unable to visit or even see most of reality. Humbling, awe-inspiring. The universe is vast, beyond comprehension, and we've barely begun exploring our tiny corner of it. The cosmological horizon marks the edge of what we can observe. Beyond it lies the unknown, regions too far away for their light to have reached us. Galaxies we'll never see, stars we'll never study. Perhaps planets with life we'll never contact. The question naturally arises, what's out there? What exists beyond the boundary of observation? Scientists propose 3 main possibilities. Each has different implications for the nature of reality and our place in it. Understanding these scenarios helps us grasp what we can and cannot know about the cosmos. The first possibility is homogeneity. The universe beyond our horizon continues much like the universe within it. Same laws of physics, same types of galaxies, same distribution of matter and energy, same dark matter and dark energy. Everything we see here extends everywhere. The cosmological principle taken to its logical conclusion. The cosmological principle states that on large scales, the universe looks the same in all directions and from all locations. No preferred center, no special places, homogeneity, and isotropy. This principle has guided cosmology for a century. It simplifies equations, makes the universe tractable mathematically, and observations support it. The cosmic microwave background is nearly uniform. Galaxy distributions appear similar in all directions when averaged over hundreds of millions of light years. If the cosmological principle holds universally, beyond our horizon we'd find more of what we see here. More galaxy clusters connected by filaments, more voids between them, more stars forming and dying, more planetary systems, perhaps more life arising on suitable worlds. The universe would be vast but comprehensible. What we learn from our observable patch applies everywhere. The laws we discover here govern everything everywhere. This is the conservative view. The safe bet. Occam's razor suggests we shouldn't multiply hypotheses unnecessarily. If the observable universe appears homogeneous, why assume it changes beyond visibility? Extending known patterns is simpler than inventing new ones. Most cosmologists lean toward this interpretation. The universe is probably more of the same, boring in its sameness, comforting in its predictability. But there's no proof. We observe only our patch. We see homogeneity on scales up to billions of light years. But scales beyond that remain unknown. Perhaps homogeneity breaks down at larger scales. Perhaps our observable universe represents one small region in a much larger structure with variations we can't detect. The second possibility involves variations beyond the horizon. The universe might not be perfectly uniform everywhere. Different regions might have different properties. Some areas could be denser, packed with more galaxies, rich in matter. Other regions could be emptier than the largest voids we observe, vast stretches with almost nothing. The density of dark matter might vary. Some regions might have more, some less. This would affect structure formation. Regions with more dark matter would develop more pronounced cosmic webs. Regions with less would remain more diffuse. Dark energy could also vary. If dark energy isn't the cosmological constant but something that changes across space, different regions could have different expansion rates. Some areas might expand faster, some slower. This creates a complex universe with diverse properties depending on location. We happen to inhabit a region with particular values. Other regions would look different. Temperature could vary too. The cosmic microwave background in our observable universe sits at 2.725 Kelvin. But beyond the horizon, the CMB temperature might differ slightly. Regions that underwent different expansion histories could have different thermal properties. These variations would be subtle. Physics constrains how much variation is possible, but subtle differences could accumulate over cosmic scales. Even physical constants might vary spatially. The fine structure constant governs electromagnetic interactions. If it changes across the universe, chemistry would work differently in different regions. Atoms would have different properties. Stars would burn at different rates. Life, if it arose, might be based on different chemistry. This remains speculative. No evidence suggests constants vary. But we can't rule it out beyond our observable patch. Variations could explain some mysteries. The Hubble tension, the discrepancy in expansion rate measurements, might arise if the local universe differs slightly from the average. Perhaps our region has slightly unusual density or dark energy properties. Measurements based on local objects would differ from those based on the early universe averaged over all regions. The tension resolves if the cosmological principle doesn't hold exactly. Some theoretical models predict variations. Eternal inflation suggests different regions underwent inflation for different durations. This creates domains with different properties. Our observable universe sits entirely within one domain. But beyond the horizon, other domains might exist. Transitions between domains would be unobservable. Each domain would appear homogeneous to inhabitants, but the universe as a whole would be heterogeneous. The third possibility is the most radical, the multiverse. Our universe might be one bubble in a vast ensemble, a collection of causally disconnected regions, each potentially with different physical laws. This idea arises from certain interpretations of inflation and string theory. In eternal inflation, quantum fluctuations cause some regions to stop inflating while others continue. Stopped regions become bubble universes. Continued inflation creates more space where new bubbles can form. The process never ends. Infinite bubbles in infinite inflating space. Each bubble could have different properties, different force strengths, different particle masses, different numbers of dimensions, different versions of the standard model. These aren't just quantitative differences, they're qualitative. The fundamental physics could be different. One universe might have strong nuclear forces making nuclei very stable. Another might have weak electromagnetic forces making atoms huge and chemistry completely different. Another might have different spatial dimensions, making geometry unrecognizable. String theory provides a landscape of possible vacuum states, perhaps 10 to the power of 500 different configurations. Each configuration corresponds to different physical laws. If the multiverse is real, different bubbles could sample different configurations. Our bubble happens to have the configuration we observe. Other bubbles have others. Most configurations probably don't support life. No stars, no planets, no complexity. We exist in a bubble that permits our existence. Anthropic reasoning. We couldn't observe universes where observers can't exist. The multiverse is controversial. Many scientists reject it, not because it's implausible, but because it's untestable. Science requires testable predictions. The multiverse makes no testable predictions about our universe beyond what inflation already predicts. Everything we observe could be explained within a single universe. The multiverse adds unnecessary complexity. It raises the question, if we can't observe other universes, is the concept even meaningful scientifically? Supporters argue the multiverse might be inevitable given certain theories. If inflation is correct and operates the way models suggest, eternal inflation follows naturally. Bubble formation becomes unavoidable. The multiverse isn't an extra hypothesis. It's a consequence of theories developed for other reasons. String theory's landscape exists regardless of whether we like it. If physics leads to these conclusions, we should follow where the math goes. Philosophical implications are profound. If the multiverse exists, many questions about our universe become trivial. Why do constants have the values they do? Because other bubbles have different values. We exist in one where values permit life. Why is the universe so large? Because our bubble is this size. Why does dark energy have its specific strength? Because it varies across bubbles. Fine-tuning problems dissolve. Everything becomes environmental, contingent, accidental. But this satisfies some and frustrates others. Some scientists seek deeper explanations. They want to know why the universe is the way it is from first principles. Not anthropic reasoning, not environmental selection. Fundamental laws determining everything. The multiverse seems to give up on that quest. It says some questions have no deeper answers, just random variation across bubbles. Whether beyond our horizon lies more of the same variations or a multiverse, one thing is certain, we'll never know directly. Observation is impossible. Light from beyond the horizon hasn't reached us. Due to accelerating expansion, it never will. These regions are permanently beyond access. We can speculate. We can build mathematical models. We can extrapolate from what we see, but we can't verify. Science reaches its limit at the horizon. This bothers some people. They want complete knowledge, full understanding. The horizon denies that. It imposes humility, forces us to accept ignorance, not temporary ignorance that future technology might overcome. Fundamental ignorance built into the structure of space-time. The universe keeps secrets. Some knowledge is forever beyond reach. Yet this limitation doesn't diminish what we can learn. Within our observable universe, countless questions remain. We don't understand dark matter. We don't understand dark energy. We don't know if life exists elsewhere in our galaxy. We haven't explored even our own solar system thoroughly. The horizon sits 46 billion light-years away. We're studying objects millions and billions of light-years distant. But right here in our cosmic neighborhood, mysteries abound. The horizon reminds us how much we don't know, but it doesn't constrain what we can discover. For centuries, maybe millennia, humanity will uncover new phenomena within the observable universe. The horizon won't hinder that. It only limits ultimate knowledge, knowledge of everything, everywhere. Perhaps that's appropriate. Perhaps complete knowledge would be boring. Perhaps the universe is more interesting with mysteries we can't solve. Beyond the horizon might lie infinite worlds, or nothing special. We'll never confirm which. That uncertainty is part of the human condition. We exist in a cosmos we can only partially observe. We piece together understanding from limited data. We extrapolate, we theorize, we imagine, but we can't know everything. And maybe that's okay. Maybe striving to know more while accepting we'll never know everything is what makes the scientific endeavor meaningful. The horizon doesn't end science. It defines its scope. Within that scope lies a lifetime of discovery. We return to the fundamental question, the one that started this journey. If the universe expands, what is it expanding into? You've heard about Hubble's discovery, dark energy's acceleration, the cosmological horizon, gravity versus expansion, what lies beyond observation. But we still haven't fully answered the core question, because answering it requires understanding what space actually is. And that's where things get truly strange. Space seems simple, the emptiness between objects, the stage where matter and energy perform, 3 dimensions extending in all directions, up, down, left, right. Forward, backward, we move through space. Objects occupy space. Waves propagate through space. Space is just there. Background, container, arena. But general relativity changed everything. Einstein showed that space isn't passive. It's dynamic. It curves around massive objects. It can stretch. It can compress. Space is a physical entity with properties and behaviors. So when the universe expands, space itself grows, not objects moving through space. Space between objects increasing. The fabric of reality stretching. But this leads to the question, if space grows, where does the new space come from? If a balloon inflates, it expands into the surrounding air. If a city grows, it spreads into surrounding countryside. Everything we know that expands does so into something else. Pre-existing space, empty volume waiting to be filled. The universe expanding should work the same way. Right? Wrong. Because the universe contains all space, by definition. If the universe is everything that exists, there's no external space for it to expand into. The universe doesn't expand into anything. It just expands. Space increases without needing somewhere to go. This concept violates intuition. Our brains evolved to understand medium-sized objects at human speeds, not cosmic geometry, not expanding space-time. We have no direct experience with space itself growing, so we struggle to visualize it. Here's an analogy that might help. Consider the surface of a balloon again. But this time, imagine you're a two-dimensional being living on the surface. You can move around the balloon's surface. Forward, backward, left, right. But you can't move into the third dimension. You don't even know the third dimension exists. Your entire universe is the two-dimensional surface. Now the balloon inflates. The surface area increases. From your perspective, space is expanding. Points on the surface move farther apart. But the surface isn't expanding into anything you can observe or measure. There's no outside in your two-dimensional reality. The surface just grows. Our situation might be similar. We exist in three spatial dimensions. We observe space expanding, but space isn't expanding into a fourth spatial dimension we can detect. It's simply growing. The total volume of space increases. Distances increase, but there's no external arena, no pre-existing void, no larger container. The universe is all there is. Space expansion happens within the universe itself. This leads to another question. Is the universe infinite or finite? If space goes on forever, infinite in extent, then expansion means what exactly? You can't make infinity bigger. Infinity is already infinite. So what does it mean for an infinite universe to expand? The answer, distances between objects increase. Even in infinite space, galaxies are separated by finite distances. Those distances grow. Expansion doesn't make infinity larger. It stretches the contents. Objects move farther apart. Density decreases. Temperature drops. But space remains infinite before, during, and after expansion. If the universe is finite, space has a total volume, a measurable size. Expansion increases that volume, makes the universe bigger. But bigger within what? Within itself. A finite universe doesn't need external space to expand into. It grows internally. Its volume increases by creating more space internally. Think of it like this. Imagine space has a property. Let's call it spaciness that can intensify. More spaciness means more volume. Expansion increases spaciness everywhere simultaneously. The universe doesn't push outward into external void. It intensifies inward. Observations suggest the universe is very close to flat. Flat geometry means parallel lines stay parallel forever. Euclidean geometry, the kind we learn in school. Flat space can extend infinitely, or it could be finite but unbound, like a torus. Imagine a video game where moving off the right side of the screen brings you back on the left side. The game world is finite but has no edge. Travel far enough in one direction, you return to your starting point. The universe could work similarly. Finite total space, but no boundary, no wall where space stops. Current measurements suggest that if the universe has curvature, it's less than 0.4%, essentially flat within measurement uncertainty. This flatness is itself puzzling. Why would the universe be so precisely balanced? Why not obviously curved? Cosmic inflation explains this. In the first fraction of a second after the Big Bang, space expanded by a factor of at least 10 to the 26th. That's 1 followed by 26 zeros. Any initial curvature got stretched flat, like inflating a balloon until its surface looks perfectly flat locally. Even if the balloon is curved globally, a small patch appears flat. We might live on a curved universe so large that our observable patch seems flat, but we're talking about expansion. Let's get more specific. When space expands, what actually happens? Imagine two galaxies separated by 1 billion light-years. Space expands. A year later, they're separated by 1 billion and 70 million light-years. 70 million light-years of new space appeared between them. Where did that space come from? How did it come into existence? These questions assume space is made of something, that it has substance requiring creation. But space might not work that way. In quantum field theory, space is filled with fields. Electromagnetic field, electron field, quark fields. These fields exist everywhere. They have energy even in vacuum. Virtual particles constantly pop in and out of existence due to quantum fluctuations. Vacuum isn't empty. It seethes with activity at quantum scales. When space expands, Fields expand with it. More field volume, more vacuum energy. This might be what dark energy is, energy inherent to space itself. As space grows, dark energy grows proportionally. This drives accelerating expansion. The more space exists, the more dark energy exists, the faster expansion occurs. Positive feedback, but this raises questions about energy conservation. If space creates more dark energy as it expands, where does that energy come from? Doesn't energy conservation forbid creating energy from nothing? In general relativity, energy conservation is complicated. It works locally but not necessarily globally in expanding space. Expansion changes the reference frame. Energy can be created or destroyed when space-time geometry changes. Strange, counterintuitive, but mathematically consistent. Some theories propose that space has structure at the smallest scales. Below the Planck length, about 10 to the minus 35 meters, space might not be smooth. It could be grainy, discrete, made of tiny, indivisible units, like pixels on a screen. Zoomed out, the screen looks continuous. Zoomed in, you see individual pixels. Space might be similar. At observable scales, smooth and continuous. At Planck scales, granular and discrete. This is quantum gravity territory. Speculative, unproven, but fascinating. If space is quantized, expansion means something different. Instead of continuous stretching, expansion adds more space quanta, like adding more pixels to an image. The image gets bigger by increasing pixel count, not by stretching pixels. Space might expand by creating more fundamental space units. Where do these units come from? Quantum fluctuations might generate them, or they might emerge from deeper structures we don't understand yet. String theory suggests space has extra dimensions we don't experience. Perhaps expansion involves these hidden dimensions. Compactified dimensions unrolling slightly, extra space becoming available. Pure speculation at this point, but fun to consider. There's also the concept of quantum foam. At Planck scales, quantum uncertainty dominates. Space and time become fuzzy. Virtual black holes form and evaporate. Wormholes might connect distant regions. Topology fluctuates. Space becomes a seething, chaotic landscape, not the smooth emptiness we perceive. Expansion might interact with quantum foam in ways we don't understand. Perhaps expansion smooths quantum fluctuations, or perhaps quantum foam resists expansion, creating drag. These ideas remain theoretical. No experiments can probe Planck-scale physics yet. We lack the technology and the energy. Returning to the main question, what is the universe expanding into? The answer remains nothing, because into implies external space, space outside the universe. But the universe is all space. There's no outside, no external void, no pre-existing nothingness waiting to be filled. The universe expands by creating more space within itself. Space grows, distances increase, but there's no boundary being pushed outward, no frontier advancing into external territory, just internal growth, more spacious space. This is hard to accept. Our intuition demands containers. We think in terms of objects in space, not space itself changing, but space is dynamic. It responds to matter and energy. It curves. It stretches. It's not a fixed stage. It's an actor in the cosmic drama. Understanding this requires letting go of everyday intuition, embracing mathematical descriptions, even when they conflict with common sense. Another way to think about it, the universe doesn't exist in space. The universe is space, space plus everything in it. There's no separate arena where the universe sits. The universe contains the arena. It is the arena. Expansion increases the arena from within, by its own internal dynamics, driven by its own energy content. No external influence needed, no external space required. Some people ask, could the universe be expanding into higher dimensions? Could there be a fourth spatial dimension we don't perceive? String theory proposes 10 or 11 dimensions total, most compactified to tiny scales, undetectable. Could expansion involve unrolling these extra dimensions, making them larger, creating more space that way? Possible. But even if true, those extra dimensions are part of the universe, part of space-time, not external to it. So expansion still occurs within the universe, not into something outside it. The question, what is the universe expanding into, assumes the wrong framework. It assumes the universe is an object in space, but the universe is space. All of it. The question is like asking what's north of the North Pole. There is no north of the North Pole. North loses meaning at the pole. Similarly, outside the universe loses meaning. The universe is everything. Outside doesn't exist. The question is linguistically coherent but conceptually meaningless. This doesn't mean we can't understand expansion. We can. We measure it. We model it. We predict its future behavior. We just can't visualize it using everyday analogies. Our brains aren't equipped for that. We evolved to throw spears and gather berries, not to understand cosmological expansion. But that's okay. Mathematics describes what intuition cannot grasp. Equations work where visualization fails. We can understand expansion intellectually, even if we can't picture it viscerally. Space is stranger than we imagined. It's not passive background. It's dynamic fabric. It grows. It carries galaxies along. It shapes the universe's structure and fate. And it does all this without expanding into anything external. Because there is no external, just the universe, just space, just the endless expanding cosmos we inhabit? This is the answer. The universe expands into nothing because nothing exists beyond it to expand into. Expansion is internal, intrinsic, self-contained. The universe grows within itself, creating its own future, its own space, its own destiny. And we're along for the ride, observing, measuring, wondering at the magnificent strangeness of it all. Space can bend. Einstein taught us this over a century ago. Massive objects warp the fabric of space-time around them. The sun curves space, and Earth follows that curvature, creating what we perceive as an orbit. Black holes curve space so severely that nothing escapes. But there's another kind of curvature, global curvature, the overall shape of the entire universe. And this shape determines everything about cosmic fate. Imagine you're drawing a triangle. On a flat piece of paper, the angles add up to 180 degrees. Always Euclidean geometry, the geometry we learn in school. Now draw that same triangle on a sphere, like Earth's surface. Start at the North Pole. Draw a line down to the equator. Follow the equator for a quarter of the way around. Draw another line back up to the North Pole. You've created a triangle, but measure the angles. They add up to more than 180 degrees. The triangle is puffed outward. This is positive curvature. Spherical geometry. Now imagine a saddle. The surface curves upward in one direction and downward in another. Draw a triangle on a saddle surface. The angles add up to less than 180 degrees. The triangle is pinched inward. Negative curvature. Hyperbolic geometry. These three possibilities, flat, positively curved, and negatively curved, represent the three possible shapes for the universe, and each shape leads to a different cosmic destiny. A flat universe extends infinitely in all directions without curving back on itself. Parallel lines remain parallel forever. Space goes on without end. In a flat universe with matter but no dark energy, expansion would gradually slow down. Gravity pulls everything together, breaking the outward motion. Eventually, expansion would approach zero. The universe would coast toward a cold, dark future. But it would never collapse. It would expand forever, just slower and slower. Add dark energy to a flat universe, and the picture changes. Dark energy drives acceleration. Eventually, dark energy dominates over matter. Expansion speeds up. Galaxies separate faster and faster. The universe grows larger, emptier, colder. This is the scenario observations suggest. Our universe appears flat or very close to it, and dark energy is real, so we're headed for accelerating expansion, eternal growth, heat death trillions of years from now. A closed universe curves back on itself like the surface of a sphere. Travel far enough in one direction, and you eventually return to your starting point. Space is finite but has no edge, no boundary, like Earth's surface, which is finite in area but has no cliff where you fall off. In a closed universe, parallel lines eventually converge. Space has positive curvature. The total geometry is spherical. Closed universes have interesting properties. They contain a finite amount of space, a definite volume. You could, in principle, measure the total size. Of course, it would be enormous, trillions upon trillions of cubic light years, but finite nonetheless. A closed universe also has more matter and energy density than a flat one. Higher density means stronger gravity, and gravity changes the fate dramatically. In a closed universe without dark energy, gravity eventually wins. Expansion slows, stops, then reverses. Galaxies start approaching instead of receding. Space contracts. Everything comes back together. This is the Big Crunch, the opposite of the Big Bang. Galaxies collide, stars merge, space shrinks, temperature rises. Eventually, everything compresses into a hot, dense state, perhaps followed by another Big Bang, an oscillating universe. Cycles of expansion and contraction repeating eternally. Poetic, elegant, but probably not reality. An open universe has negative curvature, saddle-shaped geometry. Parallel lines diverge. Triangles have angles summing to less than 180 degrees. Space extends infinitely, but with a hyperbolic shape. An open universe has less matter and energy density than a flat one. Gravity is weaker. Expansion never stops. The universe expands forever, faster and faster. Even without dark energy, an open universe accelerates outward indefinitely. How do we determine which shape describes our universe? We measure curvature. Several methods exist. The most precise involves the cosmic microwave background. The CMB contains tiny temperature fluctuations, hot and cold spots. These spots have characteristic sizes determined by physics in the early universe. Sound waves propagating through primordial plasma created these patterns. The wavelength of the sound, about 1 degree on the sky, depends on the universe's geometry. In a flat universe, light travels in straight lines. The spots appear a certain size. In a positively curved universe, light paths converge. Spots appear larger. In a negatively curved universe, light paths diverge. Spots appear smaller. By measuring spot sizes precisely, we determine curvature. The Planck satellite did exactly this from 2009 to 2013. It mapped the CMB across the entire sky with unprecedented precision. The result? The universe is flat. Within measurement error, curvature is zero. More specifically, Planck found that if the universe has curvature, it's less than 0.4%. The universe might be slightly closed or slightly open, but the deviation from flatness is tiny. For practical purposes, the universe is flat. This flatness is itself mysterious. Why would the universe be so precisely balanced? Among all possible curvatures, why this special value? Cosmic inflation provides an answer. In the first fraction of a second after the Big Bang, space expanded exponentially. The scale factor increased by at least 10 to the power of 26. That's 1 followed by 26 zeros. Any initial curvature got stretched nearly flat. Think of inflating a balloon. When small, the curvature is obvious. Inflate it to enormous size, and a small patch looks completely flat. Even though the balloon overall is curved, locally it appears flat. The universe might be curved on scales much larger than we can observe. Our observable universe, 93 billion light-years across, might be a tiny patch on a much larger curved structure. If the radius of curvature is 1,000 times larger than the observable universe, we'd never detect it. The universe would appear flat to us, like ants on a basketball. To the ants, the surface seems flat. They can't see the curvature because they're too small. Inflation also explains why different regions of the CMB have the same temperature. Before inflation, the entire observable universe was smaller than an atom. All regions were in thermal contact. They equilibrated to the same temperature. Then inflation stretched them apart faster than light. They've been causally disconnected ever since, but they retain the same temperature from their pre-inflation contact. Inflation solves multiple problems simultaneously. It flattens curvature. It explains CMB uniformity. It generates density fluctuations that seed galaxy formation. The critical density determines the universe's shape. This is the exact amount of matter and energy needed for flat geometry. Calculate the critical density using the Hubble constant and fundamental constants. If actual density exceeds critical density, the universe is closed. If actual density is below critical, the universe is open. If actual density equals critical, the universe is flat. Measurements show our universe sits almost exactly at critical density. Matter contributes about 30% of critical density. This includes both ordinary matter, about 5%, and dark matter about 25%. Dark energy contributes the remaining 70%. Together they sum to approximately 100% of critical density. Flat universe, balanced on a knife edge between open and closed. This balance seems coincidental. Why should the total density equal critical density so precisely? In the early universe, even tiny deviations would have grown. If density started slightly above critical, it would have increased rapidly. The universe would have collapsed long ago. If density started slightly below critical, it would have decreased rapidly. The universe would be essentially empty by now. No galaxies, no stars, no us. But we observe near-perfect flatness. This is the flatness problem. Inflation solves it by making the universe so large that any initial curvature becomes negligible. The observable universe is a tiny, flat patch of a possibly much larger structure. Whether that structure is open, closed, or flat on ultra-large scales remains unknown. We can only measure curvature within our observational limits. If the universe is slightly closed, implications emerge. Eventual recollapse becomes possible if dark energy weakens or disappears. Billions or trillions of years from now, expansion could slow and reverse. Galaxies would stop receding. Red shifts would turn into blue shifts. The cosmic microwave background would heat up instead of cooling down. Space would contract. Galaxy clusters would merge. Eventually, all matter would compress back into a hot, dense state. The Big Crunch. Some models propose a cyclic cosmology. The Big Crunch triggers another Big Bang. The universe bounces, expands again, collapses again, bounces again. Infinite cycles stretching into the past and future. Each cycle might have slightly different properties, different physical constants, different amounts of matter. Our cycle permits life. Other cycles might not. This is speculative. No evidence supports cyclic cosmology currently, but it remains a theoretical possibility if the universe has slight positive curvature and dark energy evolves over time. If the universe is slightly open, the outcome is simpler. Eternal expansion. Even without dark energy, an open universe expands forever. Add dark energy, and expansion accelerates. The future looks similar to a flat universe with dark energy. Growing emptiness, increasing isolation, heat death. The difference between flat and slightly open is negligible for practical purposes. Both lead to cold, dark, lonely futures. Current evidence favors flat geometry with dark energy. This means accelerating expansion forever. No big crunch, no recollapse. Just endless growth. Galaxies separate, clusters isolate, stars burn out. Black holes evaporate. The universe approaches maximum entropy, absolute cold, perfect darkness. This fate seems grim, but it's trillions of years away. Time enough for countless civilizations to rise and fall, for life to explore the cosmos, for intelligence to flourish, and perhaps find ways to survive even in a dying universe. The shape of space determines destiny. Flat, open or closed. Each leads somewhere different. Measurements tell us the universe is flat or very nearly so. Inflation explains why. Dark energy ensures accelerating expansion regardless of slight curvature. We live in a universe that will expand forever, growing colder and emptier until nothing remains but isolated particles in an infinite void. Understanding this fate doesn't diminish the beauty of existence. It enhances it. We exist in a brief, brilliant moment when the universe is rich with structure, energy, and possibility. Enjoy it while it lasts. Because cosmically speaking, it won't last long. The universe is young now, still vibrant, still full of stars and galaxies. But the future is dark, literally. So we observe, we measure, we learn, and we appreciate the remarkable fact that we exist at all in this vast, expanding, ultimately doomed cosmos. The curvature of space shapes everything, and right now, that curvature is flat. The expansion is accelerating, and the universe spreads outward into an endless, empty future. Galaxies are disappearing. Right now, as you watch this video, not dying, not exploding, simply crossing a boundary beyond which we can never see them again. The light they emit gets stretched so far by cosmic expansion that it becomes undetectable. They slip beyond the event horizon, gone forever. And this process is accelerating. When we look at distant galaxies, we see them as they were billions of years ago. The Andromeda galaxy sits 2.5 million light-years away. We see it as it was 2.5 million years ago. The light took that long to reach us. A galaxy 10 billion light-years away appears as it was 10 billion years ago, when the universe was only 3.8 billion years old. Young, different, full of active star formation and dramatic events. But here's what makes expansion so profound. That galaxy 10 billion light-years away isn't 10 billion light-years away anymore. Due to expansion during the light's journey, it's now about 16 billion light-years distant. Space stretched while the photons traveled. The galaxy moved farther away, not through space but with space, and it continues moving away right now. Every second, the distance grows. Every minute, the galaxy recedes farther. The speed of this recession depends on distance. Nearby galaxies recede slowly. Distant galaxies recede quickly. The Hubble constant quantifies this relationship. Take a galaxy sitting 1 megaparsec away, about 3.26 million light-years. It recedes at roughly 73 kilometers per second, according to local measurements. Double the distance to 2 megaparsecs. The recession speed doubles to 146 kilometers per second. 10 megaparsecs, 730 kilometers per second. 100 megaparsecs, 7,300 kilometers per second. Keep going. At some distance, recession speed equals the speed of light, about 4,200 megaparsecs, or 13.7 billion light-years. Galaxies at that distance recede at light speed. Beyond that, faster than light. This doesn't violate relativity. Special relativity prohibits objects moving through space faster than light, but galaxies aren't moving through space. Space between them expands. Relativity doesn't constrain space expansion rate. Space can stretch at any speed, even faster than light. Galaxies receding faster than light pose a problem. Their light can't reach us. Imagine running on a treadmill. The treadmill belt moves backward faster than you can run forward. You're running, but you're moving backward. You'll never reach the front of the treadmill. Light from superluminal galaxies faces the same issue. Photons travel toward us at light speed, but space expands faster. The photons make no progress. They never reach us. The galaxy becomes invisible forever. This creates the event horizon, different from the particle horizon we discussed earlier. The particle horizon marks regions whose light hasn't reached us yet but eventually will. The event horizon marks regions whose light will never reach us, even given infinite time. The event horizon sits closer than the particle horizon, about 16 billion light-years away currently. Galaxies beyond this distance will never be observable. Their light is forever trapped by expansion. But even galaxies within the event horizon face grim fates. As they recede, their light gets redshifted, stretched to longer wavelengths. Visible light becomes infrared. Infrared becomes microwave. Microwave becomes radio. Eventually, the wavelength becomes so long that detection is impossible. The galaxy fades from view, not because it stops emitting light, but because the light gets stretched beyond our ability to detect it. Consider a galaxy currently at redshift Z equals 7. That means its light is stretched to 8 times its original wavelength. Ultraviolet light from hot stars gets shifted into the visible range. That's what we observe. But as expansion continues, this galaxy recedes farther. Its redshift increases to z equals 10, then 20, then 100. At redshift 100, wavelengths are stretched 101 times. Visible light becomes far infrared. Ultraviolet becomes visible, but the total energy decreases. The galaxy dims. At redshift 1000, it's essentially invisible. Too faint, too redshifted, gone. The rate at which galaxies cross the event horizon depends on dark energy's strength. If dark energy remains constant, the event horizon stays at roughly 16 billion light-years. Galaxies currently beyond that distance will never become visible. Galaxies currently within it remain observable for now, but will eventually cross it as expansion accelerates. In the far future, most galaxies will have disappeared. How many galaxies are we talking about? The observable universe contains roughly 2 trillion galaxies. That's current estimates. 2 million galaxies, each containing hundreds of billions of stars. The total number of stars in the observable universe exceeds the number of grains of sand on all Earth's beaches. Incomprehensibly vast, yet most of these galaxies will disappear. The local group provides our cosmic lifeline. About 50 galaxies gravitationally bound together. The Milky Way and Andromeda are the giants. The rest are dwarfs. The Large Magellanic Cloud, visible from the southern hemisphere as a fuzzy patch, contains about 10 billion stars, small compared to the Milky Way's several hundred billion, but still a galaxy. The small Magellanic Cloud is smaller still. Then there are dozens of tiny dwarf galaxies, some containing only a few million stars, barely qualifying as galaxies, more like overgrown star clusters. Gravity holds the local group together. Our collective mass creates binding energy strong enough to resist cosmic expansion. The Milky Way and Andromeda approach each other at 110 kilometers per second. They'll collide in about 4 billion years, merge into a single massive elliptical galaxy, Milkomeda. The dwarf galaxies will orbit this merged giant. Some will be absorbed, others will remain satellites, but the local group as a whole stays intact. Beyond the local group lies the Virgo cluster, about 55 million light-years away, contains over 1,000 galaxies. Massive, gravitationally bound, but not bound to us. The Virgo cluster recedes. Expansion carries it away. We'll never lose sight of it completely. It's close enough that light will always reach us, but it will redshift, fade, become harder to study. In the distant future, observing Virgo will require enormous telescopes and integration times. Farther out, the Coma cluster, about 320 million light-years distant, contains thousands of galaxies. Receding faster, will remain observable for billions of years, but eventually it too will fade. The Sloan Great Wall, a massive structure of galaxies spanning 1.4 billion light-years, currently observable, will become increasingly difficult to study, eventually impossible. Fast forward 100 billion years. What does the sky look like? Most galaxies have crossed the event horizon, disappeared. The Milky Way and Andromeda have merged. The local group is now a single large galaxy with satellite dwarfs. That's all an observer sees. The rest of the sky is black, empty. No distant galaxies, no galaxy clusters, no large-scale structure, just darkness. Even worse, the cosmic microwave background has faded, redshifted beyond detectability. The CMB, that faint echo of the Big Bang, currently at 2.725 Kelvin and microwave wavelengths, will be stretched to radio wavelengths and temperatures near absolute zero. Instruments won't detect it. Future astronomers won't know it exists. What does this mean for future cosmology? Observers 100 billion years from now will face a crisis. They'll see one large galaxy surrounded by emptiness. No evidence for cosmic expansion. No evidence for the Big Bang. No CMB. No distant galaxies receding. Their observations will suggest a static universe. Small, eternal, unchanging. They'll develop completely different cosmological models. Models that fit their observations but miss the bigger picture entirely. They might conclude their galaxy is the entire universe. That space extends infinitely, empty and dark in all directions. They'll wonder why only their galaxy exists, why so much empty space surrounds them. Some might speculate about a creator making a single galaxy in an infinite void. Others might propose their galaxy has always existed and will always exist. Static cosmology. No beginning, no end, just eternal existence. These future cosmologists would be wrong, but they'd have no way to know. The evidence for the true history of the universe will have vanished. Cosmic expansion erased its own proof. The universe evolved into a state that hides its past. Information was lost irretrievably, not destroyed, just moved beyond reach, beyond the event horizon where observation is impossible. This raises a profound question. What are we missing right now? What evidence has already disappeared? Are we developing incomplete models because crucial information crossed the event horizon before we could observe it? Perhaps phenomena that occurred in the early universe left no trace we can detect. Perhaps structures exist beyond our horizon that would change our understanding if we could see them. We assume our observations sample the universe fairly, but what if they don't? Consider the Hubble tension. Two methods give different expansion rates. Maybe the local universe differs from the average. Maybe our observable patch has unusual properties. Properties influenced by structures beyond our horizon that we'll never see. Maybe resolving the tension requires information we can't access, forever unknowable. This is speculative, but unsettling. The disappearance of galaxies also affects our ability to study the universe's history. Currently, we observe galaxies at different distances and redshifts. Each distance corresponds to a different cosmic epoch. Nearby galaxies show us the recent past. Distant galaxies show us the early universe. We piece together cosmic history by observing this range. But as distant galaxies disappear, we lose windows into the past. Future astronomers will have fewer temporal samples, reduced ability to reconstruct cosmic evolution. Imagine historians losing access to older documents over time. First, records from 1,000 years ago disappear, then 500 years, then 200. Eventually, only recent history remains accessible. Future historians would struggle to understand how society evolved. They'd miss crucial transitions, key developments, foundational events. Cosmology faces the same problem as galaxies disappear. The universe actively erases its own history. Some galaxies are already effectively gone. Galaxies at redshift 11 or 12, observed by the Hubble and James Webb telescopes, represent the edge of observability. They're extremely faint, require enormous integration times and sophisticated instruments. In a few billion years, these galaxies will be undetectable, even with far better technology. They'll cross the threshold, become part of the unobservable universe, part of the past we can never study. The local group becomes our cosmic lifeboat, an isolated island in an ocean of expanding emptiness. Everything outside slowly fades away, redshifts into invisibility, crosses horizons, disappears. We're left alone, cosmically speaking. No neighbors within reach, no other structures to visit or study, just our merged galaxy and its satellites, floating in infinite darkness. This isolation might seem depressing, but it's also awe-inspiring. We exist in a golden age, a brief window when the universe is observable, diverse, and accessible, when we can see billions of galaxies, study cosmic history, map large-scale structure, measure expansion, test cosmological models. Future civilizations won't have this privilege. Past civilizations, if they existed, would have been too early. Structures hadn't formed yet. The universe was too young, too uniform, too simple. We're here at exactly the right time. Not too early, not too late. When the universe is complex enough to be interesting, but not so expanded that evidence disappears. This timing seems remarkable, perhaps anthropic. Intelligent observers require certain conditions: stars, planets, chemical elements. These conditions arise only after the universe evolves sufficiently. By the time observers appear, the universe is already old enough that some information has disappeared, but not so old that everything is gone. We observe a universe balanced between youth and age, between information-rich and information-poor. The fate of distant galaxies teaches us about the universe's transient nature. Nothing lasts, galaxies separate, light fades, information vanishes. Even the grandest structures eventually dissolve into isolation. The cosmos that seems so eternal, so unchanging on human timescales, is actually dynamic and temporary. Give it enough time, and everything changes, everything ends, even the ability to know that anything ever existed outside our local neighborhood. The universe moves toward a future where observers, if any exist, will be cosmically blind, trapped in isolated pockets, unable to see beyond, unable to know what they're missing. We should appreciate our cosmic visibility while it lasts, because cosmologically speaking, it won't last forever. Fast forward 1 trillion years into the future, the universe looks nothing like it does today. The sky has darkened. Most galaxies have disappeared beyond the event horizon. The Milky Way and Andromeda merged into Milkomeda billions of years ago. But something more profound has happened. The stars are dying, one by one, generation after generation, and they're not being replaced. Star formation requires raw materials, hydrogen gas primarily. Clouds of gas collapse under gravity. The center heats up. Nuclear fusion ignites. A star is born. This process has repeated countless times since the first stars formed, about 13 billion years ago. But gas clouds don't last forever. Stars consume hydrogen, convert it to helium. Heavy stars fuse helium into carbon, oxygen, and heavier elements. But eventually the fuel runs out, the star dies, and the gas it returns to space gets recycled into new stars. The cosmic recycling program that has sustained star formation for billions of years. But recycling isn't perfect. Some gas gets locked away in stellar remnants, white dwarfs, neutron stars, black holes. Each generation of stars removes gas from circulation. Slowly, the available material decreases. Star formation slows. Fewer new stars ignite. The peak of star formation occurred about 10 billion years ago. The universe was younger, denser, richer in gas. Since then, the rate has declined, and it continues declining. In a trillion years, most star formation has ceased. The remaining gas is too dispersed, too hot, too ionized. Gravity can't collapse it efficiently. The universe still contains matter, plenty of it, but the conditions for making new stars have largely disappeared. The stellar assembly line shuts down. The last stars form, shine briefly, then die, leaving behind only their corpses. What types of stars survive longest? Small ones, red dwarfs, stars with masses between about 8% and 50% of the Sun. These stars burn their fuel slowly, very slowly. A red dwarf with 10% the Sun's mass will shine for 10 trillion years. Compare that to the Sun's 10 billion year lifespan. Red dwarfs are conservative, miserly with their fuel. They'll outlast every other type of star by factors of hundreds or thousands. But even red dwarfs eventually exhaust their hydrogen. When they do, they don't become red giants like the Sun will. They're too small. They simply cool down, gradually, over billions of years. They become white dwarfs, dense stellar remnants about the size of Earth, but with masses comparable to the Sun. White dwarfs don't fuse anything. They're just hot cores slowly radiating away their thermal energy, cooling from tens of thousands of Kelvin down toward absolute zero. In a trillion years, most stars in Milky are white dwarfs. The galaxy contains perhaps 100 billion of them, remnants of sun-like stars and red dwarfs that exhausted their fuel. They glow faintly, dim embers scattered through the galaxy. The brightest ones shine with a tenth the luminosity of the present-day Sun. The coolest barely emit visible light, just infrared radiation. The galaxy appears dark compared to today. No brilliant blue giants, no vibrant star-forming regions, just the dying glow of stellar remains. Some stars ended more dramatically. Massive stars, more than 8 times the Sun's mass, exploded as supernovae. These explosions left behind neutron stars or black holes. Neutron stars are incredibly dense. A teaspoon of neutron star material weighs 1 billion tons. They're only about 20 kilometers across, but contain more mass than the Sun. Neutron stars spin rapidly when formed, pulsars, beaming radiation like cosmic lighthouses. But over millions of years, they slow down. The magnetic fields decay. The beams weaken. Eventually, they become invisible, silent, just compact balls of neutrons slowly cooling. Black holes are even stranger. Stellar mass black holes form from the most massive stars. They're gravitational prisons. Once something crosses the event horizon, it can never escape. Black holes don't emit light. They're perfectly black, invisible except for their gravitational effects on nearby matter. In a trillion years, Milky contains millions of stellar mass black holes, scattered throughout the galaxy. Most are solitary. Some orbit each other in binary systems. Occasionally, 2 black holes merge, creating gravitational waves that ripple through space-time. The galactic center hosts something far more massive, a supermassive black hole. Milky's central black hole weighs billions of solar masses, inherited from the Milky Way and Andromeda's central black holes, which merged during the galactic collision. This monster dominates the galaxy's inner region. Stars and stellar remnants orbit it. Occasionally, one ventures too close. The black hole's tidal forces rip it apart. A brief flare of radiation, then silence. The black hole consumes the debris. By 10 trillion years, the last red dwarfs have exhausted their fuel. Star formation ceased long ago. The galaxy contains only stellar remnants, white dwarfs, neutron stars, black holes, brown dwarfs, failed stars that never achieved fusion, wander through space. Planets orbit dead stars or drift freely after their stars expired. The galaxy is dark, cold, dead, but the universe continues evolving. White dwarfs keep cooling. After 10 trillion years, the hottest ones have temperatures around a few thousand Kelvin, glowing dull red. Most are cooler. Eventually, after hundreds of trillions of years, white dwarfs cool to the temperature of the cosmic microwave background, about 3 Kelvin currently, but much colder in the far future due to cosmic expansion. These cooled white dwarfs are called black dwarfs, completely dark, radiating no detectable light, just cold lumps of degenerate matter drifting through space. Black dwarfs can last an extraordinarily long time, trillions upon trillions of years, but even they don't last forever. Quantum mechanics allows processes that seem forbidden classically. Protons, the building blocks of atomic nuclei, might decay. Current experiments set a lower limit on proton lifetime, at least 10 to the 34 years. That's 1 followed by 34 zeros, far longer than the current age of the universe. But if protons decay, matter eventually disintegrates. Imagine waiting 10 to the 35 years. By then, 10, most protons in black dwarfs have decayed. The black dwarfs evaporate, slowly, atom by atom, particle by particle. They shed mass through proton decay and other quantum processes. After 10 to the 40 years, black dwarfs have largely disappeared, turned into photons and lighter particles. The galaxy, once containing 100 billion white dwarfs, now contains only scattered radiation and exotic particles. Neutron stars face a similar fate. Neutrons are made of quarks held together by the strong nuclear force. If protons decay, neutrons likely do too, though possibly at different rates. Neutron stars would evaporate over immense timescales. After 10 to the 40 years, neutron stars join black dwarfs in oblivion, dissolved by quantum decay. But black holes remain. Black holes don't decay through proton decay. They're space-time curvature, not made of particles. Yet they too face eventual destruction. Stephen Hawking discovered in the 1970s that black holes radiate. Quantum effects near the event horizon create particle-antiparticle pairs. One particle escapes, the other falls in. The black hole loses mass, very slowly. This is Hawking radiation. The rate depends on the black hole's mass. Small black holes radiate faster, large ones slower. A black hole with the sun's mass would take 10 to the 67 years to evaporate completely. That's incomprehensibly long. A supermassive black hole with a billion solar masses takes 10 to the 100 years, written out 1 followed by 100 zeros. A googol. This timescale dwarfs everything else in cosmic history by unimaginable factors. So the universe enters the black hole era. After stellar remnants decay, black holes dominate. They're the last massive objects, drifting through expanding space, occasionally absorbing stray particles, slowly radiating through Hawking radiation. The universe is dark, cold, nearly empty. Temperature hovers just above absolute zero. Entropy approaches maximum. This is the heat death scenario. Heat death doesn't mean everything gets hot. It means thermal equilibrium, no temperature differences, energy distributed uniformly. In thermodynamics, heat flows from hot to cold. When everything reaches the same temperature, heat flow stops. No energy gradients exist. No work can be done. No processes occur. The universe reaches maximum entropy, a state of perfect disorder and uniformity. Stars create order locally by concentrating energy. Planets maintain temperature differences between day and night sides. Life creates complex structures. All these processes increase local order while increasing total entropy. The universe, governed by the second law of thermodynamics, always increases in entropy. Order gives way to disorder. Structures break down. Energy spreads out. Eventually, perfect uniformity. In the black hole era, the universe consists mostly of empty space, a few black holes, scattered photons stretched to enormous wavelengths, maybe dark matter particles, maybe exotic particles we haven't discovered. Temperature everywhere is essentially the same, near absolute zero. Nothing happens. No stars shine. No planets warm, no chemistry occurs, just black holes slowly evaporating in the darkness. The final black holes evaporate in stages. First, stellar mass black holes disappear, then intermediate mass ones, finally the supermassive black holes. Each evaporation releases a final burst of Hawking radiation, a brief flicker of light in eternal darkness, then nothing. When the last black hole evaporates, the universe contains only radiation and fundamental particles, photons, neutrinos, electrons, positrons, maybe dark matter particles, all moving through expanding space, becoming more diluted, cooling further. This is the asymptotic endpoint, the far future, the ultimate fate if dark energy remains constant and protons decay. A universe consisting of nearly nothing, particles separated by vast distances, each particle alone, unable to interact with others because they're too far apart. The density approaches zero, the temperature approaches zero, entropy approaches maximum but never quite reaches it because quantum fluctuations persist. Some speculate about what happens after this. Maybe quantum tunneling creates new universes. Maybe space-time itself fluctuates enough to spawn baby universes. Maybe the vacuum state isn't stable and eventually decays into something else. These ideas are highly speculative, untestable, perhaps unknowable. The standard model of cosmology simply says expansion continues forever, temperature decreases forever, density decreases forever. The universe becomes increasingly empty, cold, and dark without end. This fate seems bleak, depressing even. The universe, now so full of light and structure, will end in absolute darkness and isolation. Every star will die, every galaxy will disperse, every black hole will evaporate. Everything we know and cherish is temporary, doomed to fade into oblivion over time scales that make the current age of the universe seem like an eye blink. Yet there's strange beauty in this inevitability. The universe had a beginning. It will have something resembling an end, though expansion continues eternally. From hot, dense simplicity to cool, diffuse simplicity. The middle, where we exist, is the interesting part. The brief era of complexity, structure, and life. We're witnesses to the universe's middle age, after childhood but before senility, when things happen, when stars shine and galaxies swirl and life emerges and wonders about its place in the cosmos. The heat death is trillions of years away. For now, stars still burn, galaxies still form, life still evolves. The universe remains a place of incredible richness and possibility. Understanding the distant future doesn't diminish the present, it illuminates it. We're here during the universe's most dynamic era, the age of stars and galaxies, the age of observers, the age of questions and discoveries. That's worth appreciating, even knowing it won't last forever. The laws of physics seem eternal and unchanging. The speed of light is 299,792 458 meters per second, always, everywhere. The gravitational constant determines how strongly masses attract. The fine structure constant governs electromagnetic interactions. These numbers appear fixed, carved into the fabric of reality. But are they? Could cosmic expansion, particularly accelerating expansion driven by dark energy, alter these fundamental constants over time? Could the laws themselves evolve as the universe expands? This question probes the deepest foundations of physics. We assume constants are constant. The word itself implies unchanging. Yet we have no fundamental theory explaining why these constants have the values they do. Why is the speed of light exactly that value? Why is the gravitational constant what it is? Why does the fine structure constant equal approximately 1 divided by 137? These numbers seem arbitrary. No deeper principle requires them. They're measured experimentally. We accept them as given. But given by what? The fine structure constant provides the most interesting case. This dimensionless number, approximately 0.00729735256, characterizes the strength of electromagnetic interactions. It determines how strongly electrons bind to atomic nuclei, how atoms absorb and emit light. The entire structure of chemistry depends on it. If the fine structure constant were slightly different, atoms would behave differently, molecules would form differently. Life as we know it couldn't exist. Some physicists have searched for evidence that the fine structure constant changes over cosmic time. They examine light from distant quasars. These brilliant objects lie billions of light years away. Their light comes from the early universe. By analyzing spectral lines, patterns of absorption and emission, physicists can measure the fine structure constant at different cosmic epochs. If it changed over billions of years, the ancient value would differ from today's value. Results remain controversial. Some studies claim tiny variations. Others find no change within measurement uncertainty. The claimed variations are extraordinarily small, perhaps a few parts per million over billions of years. If real, they suggest the fine structure constant increases slightly as the universe ages and expands. But the evidence isn't conclusive. Systematic errors in measurements could explain the apparent variations. More data is needed. If the fine structure constant truly varies, the implications are profound. It means the laws of physics aren't fixed. They evolve as the universe evolves. What we call constants are actually variables changing on cosmic timescales. This opens extraordinary possibilities. Perhaps other constants vary too. The speed of light, the gravitational constant, the masses of fundamental particles, all potentially changing as space expands. What could cause constants to change? Several theoretical frameworks allow this. String theory proposes that fundamental particles are tiny vibrating strings. Different vibration modes correspond to different particles. The properties of these particles, including their masses and interaction strengths, depend on the geometry of extra dimensions. String theory requires 10 or 11 total dimensions. 6 or 7 are compactified, curled up so small we don't detect them. If these extra dimensions change size as the universe expands, particle properties could change too. The string theory landscape contains perhaps 10 to the 500th power possible vacuum states. Each state corresponds to different values for physical constants. Our universe occupies one state. If cosmic expansion causes transitions between states, constants could jump from one value to another, suddenly, discontinuously. This seems unlikely based on observations. We'd notice such jumps, but gradual drift between nearby states might be undetectable. Another possibility involves scalar fields. These are quantum fields that permeate space. The Higgs field is one example. It gives particles mass through interactions. Other scalar fields might exist. If such fields have energy that varies as the universe expands, their interactions with particles could change. This would alter effective masses and coupling constants. The variations would track the expansion history. Accelerating expansion driven by dark energy might enhance these effects. Dark energy itself might be a scalar field. If so, it's dynamical. It evolves over time. Its energy density changes as space expands. This changing dark energy could couple to other fields and particles, modifying their properties subtly. The fine structure constant could increase because dark energy strengthens electromagnetic interactions. stars. Gravity could weaken because dark energy opposes gravitational attraction. These speculative ideas lack experimental support, but they're theoretically possible. The speed of light occupies a special place in physics. Einstein's relativity makes it fundamental. Space and time relationships depend on light speed. Changing the speed of light would require modifying space-time structure itself. Most physicists consider this impossible. The speed of light isn't just another constant. It defines the geometry of space-time. Altering it would require new physics beyond general relativity. Yet some alternative theories allow varying light speed. These theories modify Einstein's equations. They propose that in the early universe, light traveled much faster. This helps solve certain cosmological problems without inflation. As the universe aged and expanded, light speed decreased to its current value. These varying speed of light theories face challenges. They must reproduce all successful predictions of standard cosmology while adding this new feature. Most physicists favor inflation over varying light speed, but the door remains open. The gravitational constant poses similar questions. Gravity seems weak compared to other forces. Why? The hierarchy problem. Electromagnetism is 10 to the 36th power stronger than gravity. This enormous disparity lacks explanation in the standard model. Some theories propose gravity is weak because it leaks into extra dimensions, or because we live on a brane, a lower dimensional surface embedded in higher dimensional space. If cosmic expansion affects these extra dimensions or brane configurations, gravity's strength could change. Observations constrain how much constants can vary. Solar system dynamics require the gravitational constant remain stable over billions of years. Any significant change would alter planetary orbits. Earth's orbit would shift, the moon's orbit would drift. We'd notice. Measurements show the gravitational constant is stable to better than 1 part in 10 trillion per year, essentially constant over observable time. But what about the far future? If expansion continues accelerating for trillions of years, could cumulative changes become significant? Could constants drift enough to alter physics fundamentally? Suppose the fine structure constant increases by 1% over a trillion years, barely detectable now, but after enough time, chemistry changes. Atoms become more tightly bound. Stars burn differently. The universe transforms not just through expansion and cooling, but through evolving physical laws. This raises philosophical questions. What does it mean for laws to be laws if they change? We think of laws as eternal truths, mathematical relationships that hold always and everywhere. If they vary with time and space, are they still laws, or just effective descriptions valid locally? Perhaps beneath the varying constants lies a deeper law, a meta-law that governs how constants change. This meta-law would be the true fundamental principle. The constants we measure would be derived quantities, emergent properties of the universe's state. Some physicists embrace this perspective. They argue constants shouldn't be constant. Demanding unchanging values is anthropocentric. We observe the universe at one particular moment in its history. Why expect our snapshot to represent eternal truth? The universe evolves. Why shouldn't its fundamental parameters evolve too? This view suggests physics is more like geology or biology, studying a changing system, not timeless mathematics but cosmic natural history. Others resist. They argue physics seeks eternal laws precisely because those are explanatory. Varying constants push explanation further back. Why do constants vary the way they do? What determines the variation? You need laws governing the variation. Those meta-laws become the new constants. The regress continues until you find genuinely fixed principles. Better to assume constants are constant unless forced to conclude otherwise. The anthropic principle enters here. We observe the universe that permits our existence. If constants varied wildly, complex structures couldn't form. No stars, no planets, no chemistry, no life, no observers. The fact that we're here constrains which universe we observe. We necessarily find ourselves in a universe with constants allowing observers. This doesn't explain the values, but it explains why we measure values compatible with our existence. If the multiverse exists and different regions have different constants, anthropic reasoning becomes powerful. Most universes are sterile, unsuitable for life. A tiny fraction have constants in the narrow range permitting complexity. We inevitably inhabit one of those rare universes, not by design, by observational selection. We can't exist in universes with wrong constants. So of course we observe appropriate constants. This resolves fine-tuning problems. No cosmic designer needed, just vast numbers of universes sampling all possibilities. But this explanation troubles many scientists. It seems to give up on finding deeper reasons. It It says because we exist, rather than deriving values from fundamental principles, it's unfalsifiable. We can't observe other universes to confirm they have different constants. The multiverse might be true, but it's not testable science in the traditional sense. It's metaphysics. Returning to cosmic expansion and constants. Current evidence suggests constants remain stable over cosmic history. Variations, if any, are tiny, too small to affect physics appreciably. The universe expands. Dark energy accelerates that expansion, but the fundamental laws governing matter and energy persist unchanged. Atoms today behave like atoms billions of years ago. Stars form and die following the same nuclear physics. Galaxies evolve through the same gravitational dynamics. Yet we can't be certain. Our observations cover only a fraction of cosmic history. The universe is 13.8 billion years old. We observe light from the first few hundred million years onward, but the far future remains unknown. If constants drift slowly, the changes might be undetectable over billions of years, but significant over trillions. Future civilizations, if any exist, might discover their physics differs from ours, not because they're wrong, but because reality evolved. Imagine observers in the black hole era, 10 to the 100 years from now. The universe is vastly larger, emptier, colder. Dark energy has driven extraordinary expansion. If constants vary with expansion, they might differ significantly by then. Perhaps the fine structure constant increased by 10%. Perhaps gravity weakened by 5%. These changes would make the universe even more hostile to complexity. Atoms less stable, stars impossible, only black holes remaining, and even they eventually evaporate. Could expansion accelerate so much that constants change catastrophically? This is the Big Rip scenario taken to extremes. Not just space tearing apart matter, but physical laws breaking down, constants changing so rapidly that atoms can't hold together. Electromagnetic forces weaken, nuclear forces fade. Everything fragments at the most fundamental level. The universe doesn't just die, it becomes physically incoherent. Laws lose meaning when constants vary arbitrarily. Most physicists consider this unlikely. If constants vary at all, they probably change gradually, smoothly, tracking the expansion in predictable ways. No sudden ruptures, no breakdown of physics, just slow drift barely noticeable over billions of years. The laws we discovered remain valid indefinitely, close enough to predict phenomena, good enough for engineering, perhaps imperfect in the 15th decimal place, but solid where it matters. The possibility that constants change reminds us how much we don't know. We've measured these values to impressive precision, built theories explaining vast ranges of phenomena, predicted observations confirmed repeatedly. Yet we don't understand why constants have their specific values, what determines them, whether they're truly fundamental or emerge from deeper principles. These questions remain open. Perhaps cosmic expansion provides clues. Perhaps observations over longer timescales will reveal variations. Or perhaps constants are exactly what they seem. Fixed features of reality, eternal anchors in an evolving cosmos. Either way, the question matters, because if constants change, the universe is even stranger than we thought. Reality itself becomes fluid, mutable, evolving not just in structure but in essence. The fabric of existence shifts beneath our feet. Physics becomes history, laws become contingent, and understanding the cosmos requires tracing not just how galaxies form and stars burn, but how the rules themselves emerged and might yet transform. Zoom out, far out, beyond individual galaxies, beyond clusters. Look at the universe on its largest scales. What emerges is breathtaking. A cosmic web, vast filaments of galaxies stretching across hundreds of millions of light years. Dense nodes where filaments intersect. Galaxy clusters sitting at these intersections like cities at highway junctions, and between the filaments, voids, enormous empty regions where almost nothing exists. This structure emerged from tiny density fluctuations in the early universe. Regions slightly denser than average attracted more matter. Gravity amplified small differences. Over billions of years, matter flowed along paths of least resistance, coalescing into sheets and filaments, draining from underdense regions. The voids grew emptier, the filaments grew denser, like water flowing through a sponge. The solid parts stay solid, the holes grow larger. The cosmic web spans the observable universe. The largest known structure, the Hercules Corona Borealis Great Wall, stretches across 10 billion light-years, contains billions of galaxies organized into a coherent superstructure. These walls and filaments define the universe's skeleton, the framework upon which everything hangs. But this skeleton is fragile. Expansion pulls at it, relentlessly, trying to tear it apart. Within filaments and clusters, gravity holds firm. The binding energy keeps galaxies together. They orbit common centers of mass. They interact, they collide, they merge. The local group sits on a small filament connecting the Virgo cluster to other nearby structures. We're part of this cosmic tapestry, connected to the larger web, but barely. Our thread is thin. The voids tell a different story. Here, expansion dominates completely. Almost no mass to resist. Space stretches freely. The Buta's void, discovered in 1981, contains only 60 galaxies across 330 million light-years. That's vastly underdense. Most regions that size contain thousands of galaxies. The void continues expanding, growing larger every billion years. Eventually, it will dwarf entire superclusters. As expansion accelerates, the cosmic web transforms. Filaments stretch, thin out. Galaxies along filaments find themselves increasingly isolated. Their neighbors recede. Gravitational interactions become rare. The web that once connected them weakens. Strands snap, nodes separate. The unified structure fragments into isolated pieces. This process happens slowly, over tens of billions of years, but inexorably. The voids expand faster than the filaments can maintain coherence, like pulling apart a spider web. At first it holds, the silk stretches, but keep pulling, threads break, the web disintegrates into disconnected fragments. The cosmic web faces the same fate. Superclusters represent the largest gravitationally bound structures. The Laniakea supercluster, which includes the Virgo cluster and our local group, spans 520 million light-years, contains roughly 100,000 galaxies, all flowing toward a common gravitational center called the Great Attractor. But even superclusters aren't truly bound. They're too large. Expansion is stronger than their collective gravity. Over time, they'll disperse. In 100 billion years, the cosmic web is unrecognizable. Most filaments have dissolved. Voids dominate the volume. Galaxy clusters float as isolated islands in an ocean of emptiness. Each cluster becomes its own universe effectively, separated from all others by unbridgeable distances. Light from one cluster will never reach another. They're causally disconnected, forever alone. The universe transitions from interconnected to fragmented, from a single cosmos to isolated pockets, each pocket containing a cluster or two, perhaps a few thousand galaxies, but cut off from everything else, unable to interact, unable to even observe. The cosmic web that once unified everything shatters into a trillion isolated pieces, each floating through expanding void, each blind to all others. This fragmentation represents a fundamental phase transition. The universe changes from connected to disconnected, from communicative to isolated. Information flow ceases. No signals pass between clusters. Each develops independently, follows its own evolution, experiences its own death, and none can know what happens elsewhere. The universe becomes fundamentally unknowable beyond local horizons. We're approaching the end. 2 hours of cosmic exploration, from Hubble's discovery to the universe's ultimate fate, from the question that started everything to the answer that changes everything. What is the universe expanding into? In just a few minutes, you'll have the complete answer, the final piece of this cosmic puzzle. Stay with me.